right, hello everybody, how's it going? Welcome in, welcome one, welcome all. We are back streaming some Harvard CS50X 2025. We're going to be taking a jump into week 4 on memory. So super excited to be jumping into this week in this lecture today. This lecture is going to be a long one, so we're going to be breaking it up into parts in the condensed versions. So you can I'll be uploading those shortly after, and I'm a little behind on the condensed version, so I need to upload a few more of those for week 2 and 3, and then we can go ahead and continue 4. But let's go ahead and keep it moving. We are a little bit ahead of schedule. Oh, let's go ahead and put myself on Do Not Disturb here. There we go. Hey, Mahan, how's it going? Welcome in. Welcome in. All right, let's go ahead and get the Discord. I'm going to make a note here and say all right, cool. All right, let's go ahead. Without further ado, let's jump right on into the lecture. Thanks so much for joining me here, you guys. All right, this is going to be a longer one. Oh, I need to get my headphones, though. I don't want that. Mahan, you'll have to tell me how the audio is on your end for the lecture. All right, let's get into some more C material. Can you guys not see my screen? Oh, you guys don't see my screen. Why is that? There we go. All right. Let's get started here.
This is CS50, and this is week 4 on memory, wherein we reveal a topic that's actually fairly distinct to CS50 nowadays as an introductory course known as pointers. Indeed, today is the day you can tell your friends that you learned something about pointers, and in turn, how computers work underneath the hood. I will say that this is the kind of topic, this is the kind of lecture where probably won't all sink in the first time around. Think back to that fire hose that we showed in week 0. In fact, all these years later, I still remember where I was on campus when finally today's topics finally clicked for me. It was in office hours in Elliott House dining hall in the back right-hand corner, which is only to say, as you approach this week's material, this week's problem set 4, take comfort in knowing that it is challenging. It's meant to be challenging, but as we sort of ratchet things up and up and up over the past few weeks, we will start to plateau in just about a week, and then it's sort of smooth sailing there on out, even though it might not feel that way initially this week. But this week, we'll focus all the more indeed underneath the hood at like how information is represented, like this here photograph of the bowl of stress balls that we have most every week. But recall that anytime you have an image like this, it of course is composed of pixels, and those pixels or dots each have some bits or bytes associated with them that prescribe what color those dots should be. But there's only a finite amount of information in there. So if we sort of enhance, like you don't actually see the 5, 0 more and more clearly. You only see it larger. And in fact, at this size, you can actually see the dithering, so to speak, which is sort of this cloudiness that looms over the image. And you can kind of see the outlines of the actual pixels. All of those hard vertical and horizontal edges are the pixels, the dots that compose that image. So this is actually an example of, and in fact, on this last slide here, can you see them even most clearly on the screen as we go and go and go? So how do you go about implementing then or representing something like an image? Well, there's bunches of different file formats out there for images. Like there's GIF, there's JPEGs, there's PNGs, and there's others as well. But the simplest of them, like a bitmap image, is literally just a map of bits, horizontally and vertically conceptually. So for instance, here is a grid of bits, zeros and ones. And suppose, for instance, that maybe 0 represents black and 1 represents white. Can anyone with their human eyes see what this is a picture of, even though it's just zeros and ones? Can you see it? Yeah. So it is actually a smiley face, because if the zeros are black and the ones are white, this is what's actually latent in that image. It's hard to see at this size, of course, but if we were to shrink that down and actually use square pixels, black and white, it would probably pop out all the more clearly. Of course, it's not that useful to store things with single pixels, because you can only represent two states, like 0 and 1, like black and white. And so here might be that same image actually zoomed in such that you can see all of those individual pixels. But when it comes to color, we of course need more than a single 0 or a single 1 to represent each of those pixels. We probably need like 24, maybe 3 bytes worth for some red, some green, and some blue. And recall that that's in fact one of the ideas we talked about in week 0. How do you go about representing images, for instance? So more generally, this is actually kind of an art nowadays, if only for fun, to actually use small dots and compose things on the screen. And wonderfully, just before we began today, 2 of your classmates bravely volunteered. And in fact, let me invite them to come up and introduce themselves before we reveal what they have made on this canvas here using Post-it notes, square paper, as their pixels.
Hello, my name is Selena. I'm a freshman in Wigglesworth. I'm thinking of studying robotics and possibly in secondary in AFVS.
Welcome.
Hi, I'm Jeffrey. I'm a freshman in Thayer Hall, and I'm thinking about concentrating in Econ and CS.
All right, welcome. And allow me, hang on to the microphone if you would. I'm going to go ahead and reveal what they kindly did on very, very short notice before class began. And here is what they came up with: a grid of pixels, 2 colors here. What is it that we're looking at?
Can you tell what it is? Shall we say? It's,
oh, actually, well, we can ask the audience. What is it they made? Because they're a little insecure about their pixel art. Is that it louder? Again?
A brain, a flamingo.
A flamingo?
Question mark?
Is it a flamingo? No?
No, they said a palm tree on an island.
Oh, it's a palm tree on an island. All right, maybe a round of applause for palm tree on an island if we could. Thank you. Here we go. So suffice it to say, when you do have just, thanks very much, if you have just a single color to use, black or white, and you're using 1-bit art, it's actually kind of hard to paint a picture. But if you do have actually more colors at your disposal and an even bigger grid, can you do more interesting things? And so in fact, we invited some past students to do exactly this. We shared a Google spreadsheet whereby we used the cells, instead of as long default rectangles, we just turned them all artificially into squares, so that you can use sort of the paint bucket tool and just paint different pixels onto the screen. And among the pieces of art that some of your predecessors came up with were this here, a scene from Mario using a grid of multicolored pixels. This one here of Scratch the cat. This one here in honor of the Harvard-Yale football game coming up in a few weeks' time. This one here using a bit of the same. And in fact, if you'd like to play along at home, just for fun, if you go to cs50.ly/art, you can make a copy in your own Google account of that blank spreadsheet and just play around if you'd like to experiment as well. But this is really meant to motivate one of today's topics, which is indeed how we can start to manipulate data at a lower level, including images and other things. And images, of course, can be, among other ways, be represented with RGB, some amount of red, some amount of green, some amount of blue. Before we dive into that, though, let me augment our vocabulary a bit today by adding another base to our system. So we have binary, of course, which is base 2. We have decimal, of course, which is base 10. Today, we're going to introduce one more, which is useful in today's concepts, as well as others, as we'll see down the line, known as hexadecimal, where you actually have 16 digits at your disposal. And if any of you are artistically inclined, or you might have dabbled in web development, you might actually be familiar with hexadecimal notation itself already. Here, for instance, is a screenshot from Photoshop, whereby if you use the so-called color picker to manually choose a color that you want to paint onto the screen, you see a lot of information over here. But salient to today's conversation is this here, where there's a hash sign and then typically 6 or sometimes 3 digits in this case. 000000 means that the color I'm going to get here is actually black. So it's sort of no red, no green, no blue. Hence the zeros means you're going to get black. Meanwhile, if I play around with the same color picker and I instead do FF, 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 either all caps or in lowercase, I actually get a color that we're going to see today is going to be white, which is like a lot of red, a lot of green, a lot of blue, all the frequencies of light coming together to give us what we know as white light. But now we can kind of play with this, because it's no coincidence that these are indeed 6 digits of sorts, even though they're letters of an alphabet and not numbers yet per se. For instance, FF0000 would seem to mean a lot of red and no green, no blue. And indeed, that's why we get red, according to Photoshop itself. 00FF00 gives no red, a lot of green, no blue. And of course, that's the color Photoshop would give us. And lastly, 0000FF gives us indeed blue, because that's no red, no green, but a lot of blue. So these zeros would seem to make intuitive sense here if you have no red, no green, no blue. But what's with the FF? Like FF, of course, in English are letters of an alphabet, not numbers. Well, it turns out that Photoshop and people in the world of images and people in the world of computer memory tend to use a different system altogether. They don't use binary, and no one really in practice uses binary except the computers we use, because you can't do or see much with zeros and ones alone. We humans in the real world use the decimal system again, 0 through 9, which is just very conventional. But in the context of computers, and specifically memory and files and images, we tend to use hexadecimal, which gives us another 6 digits in our vocabulary. And I'm deliberately calling them digits, even though they appear to be letters, but this is just a convention. We just we want 6 more symbols. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't want to say 10, and I don't want to write 10, because that would be 2 symbols on the screen. So the world years ago decided, all right, when we want to represent 10 with a single digit, let's call it A, and then B for 11, and then C, and then D, and then E, and then F, where F happens to be 15. So this is what's known as hexadecimal notation. And it's really the last of the notations or systems that we'll use. You can use uppercase or lowercase. The software you use kind of decides what convention to use, but they mean one and the same. So hexadecimal, hex implying 16 in this case, otherwise known as base 16. All right, so just a bit of jargon out of the way. How does it actually work mathematically? Like the exact same way as in week 0. The math is a little different. It's not going to come to you intuitively in the same way, but the system is the same. If you've got 2-digit values here, like here are some placeholders, the columns represent the 16ths to the 0th place, the 16th to the 1 place. That math is easy. This is the 1's place. This is the 16's place. Instead of in our human decimal world, 1s, 10s, 100s, or in the binary world, 1, 2, 4, 8. Same idea, just different powers for each of the columns. All right, so this number, 0, 0, represents the number you and I know as 0. In hexadecimal, 0, 1 represents the number you and I know as 1. And it goes from there pretty straightforwardly. 0, 5, 0, 6, 0, 7, 0, 8, 0, 9 translates to exactly what we know in decimal, like the number 9, because it's 1 times 9 plus 16 times 0. Gets a little more interesting when you're using 2 digits, but you're using hexadecimal, because now if I want to count as high as 10 in decimal, I would represent that in hexadecimal as 0A, 0B is 11, 0C, 0D, 0E, 0F, and there's our F. And F, I'll stipulate, just represents the number we know as 15. So 1 times F gives us 15 plus 16 times 0. All right, dot, dot, dot. We're not going to do the whole range of numbers here, but I don't want to call this 10 in hexadecimal, just like in binary. Even though you might see 1, 0, you don't say 10, you would say 1, 0. Same in hexadecimal. So this is 1, 0. But if I translate this pair of digits to decimal, what does this represent? So this is 16, because I've got 16 times 1 plus 1 times 0. And on up and on up and on up. We can sort of do this for quite a while. It gets interesting only once we get to the end. Using hexadecimal, as I've defined it, what's the highest we can count with 2 digits then in hexadecimal? FF would be the highest, because F seems to be the largest digit. So this is actually 16 times 15 plus 1 times 15 actually gives me 255. So that is as high as I can count in hexadecimal, from 00 to FF, otherwise known as 0 to 255. And if you don't believe me, quick little math will give us that. Again, 16 times 15 plus 1 times 15 as well. All right, so how is this useful, doing out this math? Well, we have the following why is this useful? So it's very common to use 2 digits of hex, maybe possibly more. Why? Well, it turns out that to represent the numbers 0 through 15, let me spread these apart now just to be deliberate about it. 0 through 15, how many bits do you need? Well, 0, you can use any number of bits. How about 15? Like how many bits do you need to count to 15? So it turns out it's 4, right? Because in binary, that would be what? The 8's place plus the 4's place plus the 2's place plus the 1, which I think gives me indeed 15. So why is hexadecimal useful? Well, it turns out that you can represent a single hex digit, whether it's 0 or F, using 4 bits, no matter what. And so why do we tend to use 2 hexadecimal digits? Well, it's just useful to be able to describe a single byte, otherwise known as 8 bits, using 2 digits instead of 8. So in binary, we'd have to use 8. In hexadecimal, we can just use 2. And it's just useful visually. Hexadecimal is useful as a result. All right, so when are we going to see this, and why are we going to see hexadecimal? Well, here's like a grid of the computer's memory, just abstracted away as byte, 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 byte in rows and columns. Well, here is how we might number those bytes. As I've stipulated for several weeks now, we could call this byte 0, this byte 1, byte 2, dot, 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 all the way to byte 15. But by convention, we don't use decimal, and we definitely don't use binary. Instead, a computer scientist would think of the addresses, the locations of, the count of bytes in memory as still starting from 0, 1, 2, 3 on up. But as soon as you get to 8, 9, A, B, C, D, E, F. Again, just a convention. There's nothing really intellectually interesting here other than we're using a different base system instead. Here's how the others might play out. And it gets a little confusing because this 1, 0 is not 10 if it's in hexadecimal. But clearly, there's some potential ambiguities here. Like, it's pretty obvious now that if you see an A through F, OK, it's probably hexadecimal. But if you see 10 or 11 or 12, well, it's maybe not. It might not be 10 or 11 or 12. Those might be hexadecimal, even though 1A, 1B is. So this is an ambiguity. And so what we're also going to see today, that the way humans have mitigated this potential ambiguity is when you write things in hexadecimal, by convention, you put a 0x before them. 0 and typically a lowercase x. That does not mean anything mathematically. It's not an extra 0 per se. It just means to the human reading this, here comes a hexadecimal number. And now there is no ambiguity. So we're going to see a lot of this today. Generally, we won't care about the numbers, but that is what we're going to be looking at, is hexadecimal. So any questions on hexadecimal, which again is just another way of representing numbers?
All right, well, we'll pause on the questions. Hello, everybody. Thanks for joining me so much. Thanks so much for joining me. Appreciate you guys. We are watching Harvard CS50X Week 4 lecture on memory. This is the 2025 version of the course. If you're a new programmer, this is a great place to start alongside me. I've been programming for half a year, teaching myself after my 9-to-5 job as a chemist. For those that don't know, I have a degree in human biology and a minor in chemistry. And I work as a chemist for the past 3 years or so. And I've been teaching myself Python and various other computer science topics pretty rigorously over the past 6 months. We've come quite far in those 6 months, and we have a long ways to go though. So yeah, how you guys doing today? Welcome in. Hey Wing Hong. Hey Tim, how's it going? Hey Insomniac. Hey Jake, how's it going? That live is really, what do you mean, Jake? Sorry, not following you there. We just turned 26 a few days ago. We had a birthday present. We passed 1,000 subscribers on this channel. We've been streaming every day for the past 2.5 months, so it's been quite the grind. Not 2.5 months. I'd say about 2 months really. Yeah, so it's been quite the grind here, but I'm enjoying it so far after my 9-to-5 job. I graduated college back in 2021, and I got a job right after that, and so now we're ready to learn some more new stuff. We're software engineer by age 28. Yeah, maybe I was thinking maybe 2 years I could give myself before I really start to try to maybe test the waters into other realms. I think maybe a good 2 years of dedicating ourselves to this craft, at least before we feel comfortable, is a good. So Tim, that does sound like a good goal, right? Thank you so much, Ari. I appreciate you so much for joining me here. Yeah. So if you're what do you guys, if you guys program or new programmers, let me know. What's your story? I really like interacting and hanging out with you guys. We have a lot of people in the community. I have a Discord linked below where we have 300 plus subscribers and followers in the Discord. A lot of you from the channel that we interact offline, and post stuff in there, and it's also a resource center for all of my study resources. As you can see in the background, I have copies of all these books. I have resources to all my notes on the lecture. Yeah. Hey, Gene, how's it going? How's it going? Hey, Gina. Hey, yeah, Jake. We already did Harvard CS50P. We're mainly taking this one for the actual computer science aspects about it. Now, I'm not taking this one to really learn about the actual programming because we already know like the basics of for loops and things like that. I think the CS50P is a great course to learn the actual syntax of programming. But in terms of now, we're just wanting to actually learn the ins and outs of computer science with memory, with bits and bytes, with image it with hexadecimal. All this stuff is crucial for continuing on, and I didn't know all this stuff before, so we got to start somewhere here. So this is a great place to start here. Let's keep going. All right, let's keep on going here. Feel free to interact in the chat. I'll try my best on the little breaks here to answer questions and such. Thank you guys so much for joining here. We're about to hit 1.1K on the channel, which is really, really exciting. So thank you guys so much for supporting here. We're really, really grinding away. It's awesome. All right, let's keep going.
Any questions?
Wait, I have a question. If anyone can answer this. So he mentioned that you put a 0x is put in front of the hexadecimal, but why was there a hashtag in front of the Photoshop example? Where is that just a representative of what Photoshop declares as? What is the difference between the hashtag that was used in Photoshop to precede the 6-digit code versus the the 0x is put in front? Anybody answer that for me? Should we ask the almighty orb? What is the difference between the 0x in front of hexadecimal versus the hashtag? The prefixes 0x and hashtag both indicate hexadecimal notation, but they're used in different contexts. 0x used in programming language like C, Python, and JavaScript to represent hexadecimal numbers. Example 0xFF, 255 in decimal, and 0x1A3, 419 in decimal. A hashtag used in CSS and design specifies specific hexadecimal colors. So in programming, okay, so let's just say a 6-digit code, a code slash, we'll say a code slash way of counting led by a this or a 0x, where the code translates to a specific color within the color spectrum or place in memory. Or numeric value. This is the 0x and this is the hashtag. Gotcha. Cool. (007A33) is my favorite hexadecimal color. Should we look that one up really fast for Tim? Show me this color. What? Show it to me. go. Come on. Show me the money. Wow, nice green. Oh, is that your color? It's over this deer. Yeah, 250, sorry, 256 total values. Yeah, that's right. Base 16, 256 total values, 0 to 255. Okay, so let's keep going here, you guys. Thank you so much, World Challenge. Appreciate that. Let's keep going.
On hexadecimal. Okay, so let's see this in practice and start to tease apart what's going on underneath the hood of our computer all of this time when we actually start to use variables and more. So here's a single line of code. Give me an integer called n and initialize it to the value of 50. So fairly straightforward. So let's actually do something with this kind of code. Let me go into VS Code here. Let me go ahead and create a program called, let's call it addresses. .c, because I want to look at the locations in memory, the address of things in memory. And let me stipulate, too, as we've said in the past, just as mailboxes in the real world, houses and buildings in the real world have unique addresses, like we were at 45 Quincy Street, Cambridge, Massachusetts, 02138, USA. Similarly, does your computer's memory have addresses, but they're super simple numbers like 0, 1, 2, ... all the way on up. So I've created a program now called addresses.c. Let's just play around with some familiar code. Let me include standardIO.h. Let me do int main void, so no command line arguments for this. Let me declare that variable n, set it equal to 50. And let's just print out n. So this is like week 1 stuff, super simple and presumably familiar by now, whereby I want to print out, using the %i placeholder, the value there of n. All right, hopefully, if no syntax errors, I can do make addresses, enter. So far, so good. /addresses, enter. And I see, as expected, the number 50. But what's actually going on inside of the computer's memory in this case? Well, we can actually see that over here. Let's look at this grid of memory here. For today's purposes, I don't necessarily know where in the computer's memory at this point the n is going to end up. So let's just arbitrarily say the computer finds room for the int in the bottom right-hand corner of my screen. The size of it is deliberate, because recall that integers tend to be how many bytes on most systems nowadays? 4 bytes by convention, aka 32 bits if you multiply by 8. So who knows? N might very well end up in the bottom right-hand corner of my screen here with the number 50 stored there. Now, it's not literally the number 50. There's literally 32 zeros and ones in the computer's memory that are turned on and off to represent the pattern that gives me the decimal number 50. So again, that's sort of week 1 style stuff, but we're thinking about now the computer's memory. In fact, even though we refer to it as n in my code, it's got to live somewhere. And the address at which it might live, for the sake of discussion, is maybe something notationally written in hexadecimal like 0x123. Completely arbitrary. In practice, it's probably a bigger number than that. But for the sake of discussion, let's assume that that 50, the variable n, just so happened to get placed by the computer at location 0x123. Can we see that in code? We haven't yet thus far. But if I propose here, maybe going back into VS Code in a moment, maybe we can actually use some slightly new syntax and poke around the contents of the computer's memory. But before we do that, we do need a few new building blocks. And there's not much new syntax today, but we're going to go pretty darn far in terms of capabilities with just a few new symbols. It turns out that in C, if you use the ampersand operator, just one of them, not two. Two means and, logically, just like two vertical bars meant or. If you use just one of them, as we are going to today, that is going to be the so-called address of operator. So you can write ampersand in the name of a variable, and the compiler essentially will tell you where that variable is in the computer's memory. And more technically, when the program is running, you will be told where it is. The star operator, or a single asterisk, is not multiply in this context. It's going to be the dereference operator, which is going to be a trick via which we can have an address and go there, sort of following a breadcrumb, following X marks the spot on a map, and going to that location in memory and just see what's there. Is it an int? Is it a char? Is it a string? Or something else? So these sort of reverse the effects of each other. This tells you the address of something. This tells you how to get to something. So the address of operator and the dereference operator, so to speak. But we need one other building block, and this one's going to be useful in the context of printf. Recall that printf has all those format codes like %s for string, %i for integer, %f for float. Turns out there's another one, %p, which is going to allow us to print what are called pointers, which are really for now synonymous with addresses in memory. So using just those new building blocks, let me propose that we do the following, leveraging this notion of a pointer. I'm going to change my code in just a moment to still have the same single line here, int n equals 50. But then let's create a second variable called p, just for convenience. But let's declare it as a pointer. A pointer is simply a variable that stores the address of something. So it's a variable that stores the address of something like OX123 or some such value. How do you use it syntactically? It's a little weird, especially since we've used star and the ampersand in other ways already. But you say that I want a variable called p. The type of this variable is going to be a pointer, so to speak. How do you express that? Well, I want it to be the address of an integer. So you say int. But you make clear that it's the address of an integer, not an actual integer per se, by putting a star here. Of all the things we have and will see in C, I will concede this is sort of the most confusing way to do this. Ideally, there would just be a variable called pointer, and you just write it, and you get a variable that's a pointer. But in the case of C, you actually specify that this variable p will indeed be an address that points to an integer. So just have to kind of let that ingrain in yourself. This one's a little easier. Ampersand n, how would you express that in English based on my previous definition? The address of n. Ampersand n just means get the address of n. And because code, recall, is generally read and executed right to left in this case, this says wherever n is, get the address of it, like OX123, and assign it to the variable p. What is the variable p? It is a pointer, so to speak. That is the address of an integer. So it is arcane, it's a little weird, but this is kind of as low level as we can get with C with just telling the computer exactly what we want to do. So let's see this. Let me go back to VS Code here. And quite simply, after clearing my terminal, let me go ahead and print out, using %p, the following address of n. And then we'll enhance this code to actually introduce, actually, no, let's do this exactly as I did. Let's go back into VS Code here. Let's declare int star p equals ampersand p, and then print out, not n itself, but print out using %p the value of p itself. So what is this going to do for me? It should print out the address of n. All right, so in my terminal window, make addresses, enter. I messed up because I did something stupid. I forgot the semicolon, as you might have one or more times the past few weeks. Let's do this again. Let's make addresses. Enter. Damn it. I screwed up a second time. I want the address of n, not the address of p. All right, so I'm doing well. So much for remembering this concept from the dining hall of Eliot House. All right, so make addresses. Enter. Oh my God, thank you. All right, so now it works.
Like me.
Hopefully, / addresses.
All
it's not going to be as simple in the actual computer is OX123. It's probably going to be a bigger number. And indeed, it's a much bigger number, but there is an address of some sort. Might be different, run on a different system, but it turns out that the variable n is stored at location OX7FFEF3C2925C, which is just a really big number that if we did all of the math on paper, pencil, or computer would be a really big decimal number. Why? The server has lots of gigabytes of memory, billions of bytes, so of course it's probably going to be a big number like that. Now I don't strictly have to create p. And in fact, let me do what my instinct had me doing a moment ago. Let me delete p and simply just print out directly what is the address of n. Let me go ahead and recompile the code, make addresses, /addresses, and I actually do get a different address this time. Why? Because I've run the program again, and things got organized in memory a little bit differently. So these numbers are not going to remain invariant, unchanged, but every time you run the program, things might deliberately or for other reasons get moved around. But all I have done is ask the computer explicitly, what is the address of n? And that's what I'm seeing. All right, so just to recap then what these lines of code are doing, previously when I had both n and p, this latter line is just asking what's the address of n, storing the address thereof in this variable p. But there's some disagreement in the world as to how you should write this syntactically. And just so you've seen it, in case you see a video or a tutorial or a book that disagrees, this is really the conventional way to write the star that means, hey, computer, this is a pointer to an integer, the address of an integer. You could also write it this way, and some people do this. I do think it's a little, this can get you into trouble in certain cases. Some people do this with spaces on either side, which even looks more like multiplication, but it's not. All three will work, but the recommended, the conventional way is indeed to do this, even though I do concede it looks a little weird, but you'll get more and more comfortable over time. All right, so if you're with me that what we've just done amounts to just figuring out where in the computer's memory a variable actually lives, I think we can poke around further to see even more of what's going on. In fact, let me go ahead and propose this. Let me propose here that we go back to VS Code here, clear my terminal window, and let's go back to the version before where I explicitly did have p. So int star p equals ampersand n, and then again, printf, quote unquote, and what I had before was %p \n, comma p. So this printed again, the exact same thing, the address of n. But what if I actually want to print out n itself, just like I did in week 0? Well, in week 0, just like I did in week 1. In week 1, I could have just done, as I did a few minutes ago, this. And this would print out, in the old school way, the value of n. And just as a quick check, make addresses, /addresses, and there's my 50 as expected. But now that I have these two other operators, whereby I have both ampersand and star, I can kind of poke around with them, play around with them in ways that should hopefully, with some practice, make sense. So for instance, I could do this again. Int star p equals the address of n. Well, I could print out n, literally as I'm doing now, or I could use the location of n, called p, and go there with the second of these two operators, the dereference operator. The dereference operator, the single star, means go to this address. And so now, when I go back to VS Code and I do make addresses, /addresses, enter, I still get 50. I'm kind of jumping through hoops proverbially here, because this is sort of the stupid, longer, more complicated way to print out the value of 50. But it just speaks to the relative power that I have by just figuring out what the address is and then going there.
You can peek at
but
the
the
address
confusing
by
part,
going
I do think about this for me and for most folks learning this, is the following. The designers of C decades ago made, I would say, the unfortunate decision to use the star in 2 different ways, and 3 different ways in total. One, multiplication. We saw that in week 1 since. But notice that there's 2 different uses of this star operator. Here, it literally means go there. Dereference the address, that is, follow the breadcrumbs and go there. But when you declare the pointer, when you create the pointer, you also use a star, but you also use the type. So what's confusing, at least to me, is that we're using the star in 2 different ways, both of which are related to addresses, both of which are related to pointers. But when you create a variable or declare a variable for the first time, you specify not only star, but the type of the pointer, just like any other variable declaration. But when you use the pointer subsequently, you do not mention the data type again. The compiler is smart enough to remember, OK, got it. You wanted a pointer to an integer. The compiler will remember that for you. You do not need to remind it. So admittedly confusing, but on line 6, we are declaring the pointer and assigning it a value. And on line 7, we are dereferencing the pointer. So one creates the pointer, one goes to that there address. So in terms of what's going on inside of the computer's memory, let me propose that if we revisit the same grid, and we propose that 50 ended up down here, the value n is actually technically at 0x123, what exactly is p, the second variable? Well, I could draw it as follows in my memory. Maybe by chance it ends up here, sort of higher up on my slide. But this is the variable called p, and the value of p is simply literally the address of n. Why is p so big? Well, it turns out on most systems nowadays, pointers, that is addresses, are 64 bits or 8 bytes. So they just use a lot of bits. Why? Well, you and I have gigabytes, again, of memory nowadays. And if you're counting up to the billions of bytes, you actually need more than 4 bytes or 32 bits. Because recall from week 0 even, the highest you can count with 4 bytes or 32 bits is 4 billion, but some of you probably have Macs or PCs that have 5 gigabytes, 6 gigabytes, 8 gigabytes or more of memory nowadays. That means we need 64 bits to count that high, so we can actually label every memory location in order to access these spots.
Okay.
So what is P? It's just a variable whose value happens to be an address. What is N? Well, it simply happens to be an integer at that address. What questions do you have on this? Yeah?
All right, we're at the questions point of view. Or the questions part, sorry. Hello, everybody. Welcome in. I appreciate you guys joining me. If you are new, my name is Michael. I'm 26 years old. I graduated college back in 2021 with a degree in human biology and a minor in chemistry. I currently work as a formulation chemist for a biotech company. And I've been teaching myself computer science more generally now for about 6 months. We've been doing it after our 9-to-5 job every day, and I've been streaming and documenting my progress, kind of like a video series, I guess, the entire time. So we started with Harvard CS50P, did a lot of reading in between then, currently reading DSA and Python, read Python crash course, made some projects, and now we're currently taking Harvard CS50X to dive deeper into general computer science, where Python lacks in the ability to kind of sugarcoats it for you. Now we actually have to learn about what's going on behind the scenes here. So it's crucial that we kind of learn this stuff to project ourselves forward. Thank you guys so much for joining me here. This is interesting, right? So we have this operator here, which is the address operator, tells you the address of something, and then the dereference operator tells you how to get to something. Tells you how to get to something. That is a terrible definition I wrote here, but so the dereference operator tells you how to get to something. Does anybody have a better definition for the dereference operator? Hey, Muhammad, thanks so much for coming in. I appreciate you for joining me here. We got a lot of chats here. I guess you mean... A byte measures digital info and equals in bits. Okay, gotcha, sorry. For addresses, yes, address, but why? Data and send data. Hey, Script Serpent, welcome in. Appreciate you joining. Awesome to hear from you again. Dereference operator is telling you, go to this address and get values stored in it. Okay. I like that. Give me more information on the dereference operator. The dereference operator is used in language like C and C++ to access the value stored at a memory location that a holder points. Yeah, exactly, like word challenge said here. Access the value at that memory. So it tells you how to get to something. So access element given an address when applied to a pointer in address in memory. This unpacks what is at that memory location. Maybe unpack is the wrong word. Maybe peek is the better word. Peaks. Sorry, peaks at that memory location. And so this references reference pointers in printf. Right, like that. Nice script serpent. That sounds awesome. What are you guys making? You guys doing a game? Okay, so in this example, what he's doing here is he's saying, I have an integer of a variable with houses the value, an integer value of 50, right? I'm going to create a pointer, which essentially unpacks the value at that pointer. Right, this is the memory address of n. So the memory address of n is assigned to this pointer, and by having this unpacking happen, applied to this pointer, when called upon, okay, no, so actually you have to have this when initialized, like he was saying, and then if you call it again, you can take a peek at that as well. So in order to create a pointer, you have to use it to declare it as a pointer to this memory location. But then to access and peek at that point, you can use it again with another functionality. Okay, so we'll say when applied to a pointer, so we'll say used to declare a variable, typically p, typically p as a pointer. When applied to a pointer, pointer in a print f, this peeks at what is at that memory location. That's what was mentioned before in the class. Yeah, you have like this two use cases of the star, to create a pointer and to dereference a pointer. So this is a dereference operator used to declare a variable, typically p, as a pointer. In like with this example, right? Like so. And then you can do like this example, we'll take this guy here from down here. Like so. And do like this example. Awesome. That looks better. Yeah, the dereference word is kind of interesting, right? It kind of is counterintuitive. That's interesting. I also have that question. Yes, a game. I worked on the settings function that was like 400 plus lines of code using header files and CPP files. Awesome, dude. Not sure what that means, but that sounds really great. All right, let's keep on moving here. We got to keep going, or we're going to be here all night.
Are you able to use more than one pointer in main? Absolutely. Just like variables, you can create as many as you want, including arrays thereof. How do you differentiate them? By way of their name. So I'm using P because it sounds like pointer, but I could call it Q or R or S or T or use an actual English word to describe my variable. I'm just using P for short. Just like any variable. Yeah?
Does the pointer have an address itself?
A good question. Does the pointer have an address itself? Short answer, yes, because anything in your computer's memory has an address, and odds are it really has 8 addresses associated with it, so maybe we refer to it by the first one or something like that. There actually exist, but we won't do this today, pointers to pointers, which answers that question. But here, I'm leaving it abstracted away and just calling it P. But it absolutely has an address. Other questions? Yeah?
You may have already said this, but when we're referencing P in the code, do we do asterisk P? Or?
A good question. When you're referencing P in your code, do you dereference it? Do you use star P? Short answer, yes, if you want to go to that location. And that is usually, as we'll see this week and next week, how pointers are useful. You want to go to that location and do something there. It is rarely, if ever, helpful to literally print or see the actual address, because who really cares? Especially if it changes every time I run my code. We as programmers don't care where things are, but that we can get to those locations. A good question. Yeah? Sorry?
Not the physical, not the actual physical memory, but the virtual.
Yes, without going down this rabbit hole today, we're talking really about virtual memory. This maps underneath the hood using virtual memory to physical memory. But for all intents and purposes, we're talking about one and the same today. Old computers, simpler times. OK, so how can we now sort of think about this? Well, that is literally what's going on in the computer's memory. But as I just said, rarely do we actually care that it's specifically at 0x123. And in fact, the name pointer kind of conjures up a nice metaphor here. Let's sort of ignore all of the bytes of memory that we're not even using or talking about anyway. And who really cares about 0x123? Let's just abstract that away, as we've done in the past, with literally an arrow when drawing or talking about these things. And just think of P as being a variable that literally points to another location in memory. So indeed, whenever a computer scientist is talking about or arguing about or designing something that involves memory, they're not going to get into the weeds of doing OX anything. They're just going to use arrows to draw things on paper or digitally. And in fact, next week, when these sort of all comes to a head when it comes to memory, we're going to build things in computers' memory known as data structures, fancier structures than simply arrays. We're going to do one-dimensional structures, two-dimensional structures, and we're going to use pointers as sort of a thread with needle to connect this location with this one, then this one, and start to create two-dimensional objects, if you will, inside of our Macs, our PCs, our phone's memory as well.
Whoa, fancy.
So to make this super clear, we actually do have a nice metaphor. Maybe if Yulia wouldn't mind coming up. I keep saying that you can think of addresses in memory as being akin to physical addresses in the real world, like mailboxes for, say, this building. Again, 45 Quincy Street in Cambridge, Massachusetts. And here then is a mailbox that has the name P. So this is appropriate, because if a pointer is a variable that stores an address, this here mailbox called P would seem to be, I'll say, storing an address. Meanwhile, Yulia has a separate mailbox here that's actually called N. So it's like a variable in memory. We're kind of cheating, because technically the pointer would be twice as big as this mailbox, but Home Depot only has so many different sizes. So they look the same physically. But N, according to the story, lives at address 0x123. So if I am the computer and I am executing code that looks like star P, go to the address stored in P, that's akin to like a person opening up a mailbox, looking inside, seeing that what's in there is not an actual value you care about per se, but it's kind of like a treasure map. X marks the spot, if we sort of abuse the metaphor, which just means if I want to go to the address in P, that means I look in computer's memory, and just to be dramatic, we can do this too. We've got a little big foam finger. This is like the computer pointing at the actual location 0x123, and voila, there is the number 50 that we care about. And for those following along at home, maybe avert your eyes here in Sanders. We can similarly do this with the Yale foam finger as well to dereference that as well. And the crowd went wild for those of you watching from New Haven today with applause. So thank you to the Yulia, though, for this particular demo. Yes, we will. We will enhance the applause in the final version of the video. So let's now revisit, admittedly, a bit of a white lie that we've been telling for a few weeks now. And I kind of tripped over this in week 1, but then sort of waved my hand and solved it real quickly by introducing the CS50 library. But I'm going to propose that we revisit what a string actually is. Now, we used strings in week 1. We then began in week 2 to talk about strings, thank you, as just being an array of characters. So that was the first reveal. But even then, we kept using the word string. But it turns out that strings do not exist in C as a data type. Strings are not a CS50 thing per se, but there is literally no keyword in C called string, string. It's a concept that exists in C, so nothing that we've said over the past few weeks has anything to do with CS50 per se. Almost every programming language you'll encounter in the real world supports strings in some way. But my claim today is that the keyword string is actually made up for us for convenience over the past few weeks. Now, why is that? Well, up until now, we have been creating strings in code with lines like this. String s equals quote unquote hi in all caps semicolon. What that would do, according to week 2's discussion of memory, is it would give us 4 bytes in memory for hi exclamation point and a 4th byte, to be clear, for the null character, NUL, the \0, which is just 0 bytes. And we therefore were able to manipulate that string as though it were an array. So s bracket 0 is the first character, s bracket 3 is the very last character, specifically that null character. Well, really, we can start to think about strings a little differently still today. In fact, let me go back over to VS Code here, clear my terminal window, and let's stop playing around with integers like number 50. And instead, let's do this. Let's give myself a string s equals quote unquote hi exclamation point. And then let's go ahead and print it out, just like in week 1 with %s \n, comma s. Let me go ahead and increase the size of my terminal window, do make addresses, and here is the very same mistake we glossed over in week 1. Error, use of undeclared identifier string, did you mean standard in? Now, maybe that does sound familiar, but it's kind of a red herring. This has nothing to do with standard in per se. String is undeclared because it doesn't exist in C by default. And in fact, it thinks maybe this is a typo. Standard in is a thing that exists in programming languages, but string, I said, in C does not. But this fix for me, recall in week 1, was to very quickly say, we'll come back to that. And at the top of my code, I went in and added one more include, CS50.h. And somehow, if I clear my terminal, rerun make addresses, that solved everything. And string was brought into existence. But how exactly was that the case? Well, we'll see today what's actually going on underneath that hood as well. So what have I just done with this code? I've simply printed out the string s. But notice, I claim, what's really going on if I visit the actual memory in the computer is, yeah, it's an array. But if an array is just a chunk of contiguous memory, certainly we could figure out what the bytes are, the addresses are of each of those characters, hi exclamation point and the null character. And again, for the sake of simple discussion, suppose the h is at 0x123, stands to reason that I is going to be at 0x124, exclamation points at 0x125, and the null character is at 0x126. The specific numbers don't matter, but what does matter is that they are 1 byte apart. And that is literally what I've meant all these weeks when I say contiguous. Back to back to back, they're literally 1 byte apart. So once we know this, can we sort of leverage this to play around with and see strings perhaps in a somewhat different light? Well, let me go ahead and do this. Let me go back to VS Code here after clearing my terminal. Let's leave string s as is, but let's print out a few different things. Let's actually print out what is inside of s. %p \n is how I can display an address, aka pointer, and let's print out the value of s. Let me go down to my terminal and do make addresses, enter, /addresses, and what I see now is a seemingly random but a much bigger hexadecimal address. So it seems that s is not a string per se, because I literally just told the computer to print it out with printf, albeit using %p instead of %s. But %p just means show me the address of a variable. And it seems that s's technical value is 0x59FB1699D004. Now, that is the longer version of what I just proposed for discussion's sake is 0x123. Well, let's be a little more pedantic here. Let me go ahead and print a couple of more things. Let me print out another address using %p. But let me print out the address of the first character in s using my array notation. And then let me do some quick copy paste just to see a few more of these. Let me print out location 1, location 2, and location 3. So we're really kind of making use of this arcane looking syntax today. Lots of %p's, but that just means show me address, 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 and so forth. S bracket 0 is from week 2. Just show me, using array notation, the first character, the second character, the third, and the fourth. And ampersand is new today. Just means show me the address of that character, not the actual character. So if I go back down to my terminal window, make addresses again, I'm going to see 5 values in total now. /addresses gives me this. Let me zoom in. And what's noteworthy is that the very first one is identical to the second one, which seems to imply that S has the same address as the first character of S. But that sort of makes logical sense, because what else would it be if not the first one? And so what we're seeing here now is a hint that whereas %p is printing out literally the value inside of S, what was %s doing all this time? It was, thanks to printf's implementation decades ago, going to that address and printing character, 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 and stopping only once printf finds what?
The escape operator or whatever.
The \0, the null byte. So some person years ago literally implemented printf. They literally are using S as an address, going to that address somewhere with a star operator in their code, and then using a for loop or a while loop, iterating over character, character, character,
come on,
character
we are getting this. I literally said that.
Until
Let's
it
go.
sees the so-called null character. All of this has sort of been happening for us automatically, but that's really all that's going on. If I go back into the visualization of my computer's memory, here's that same simplification using smaller numbers, 0x123, 124, and so forth. And what is S then when it's declared in memory? Well, it's a pointer, which means it takes up 8 bytes, so I am doing this to scale. But what is S really doing? It's storing the address of the first byte of the actual characters. It's storing nothing else. S is not storing the last byte. It's not storing the length. It's not storing anything other than the first byte's address. But that's OK. Why? Because how does the computer, functions like printf, know where the strings end? Just to be super clear.
The null character.
The \0. That's why we're wasting an extra byte all these weeks, because someone needs to know or tell everyone else where strings actually end. Those of you who do have some prior programming experience in Java or in Python or other languages, you can generally just ask a string, like, what is its length? You can call a length function. You can do .length or similar. Those of you who've done this before, that's because in higher level languages like Java and Python, there is more memory being used than just the address of the variable alone. Someone somewhere is keeping track of the length of that chunk of memory. But C is much lower level. It's much more efficient. It's much more complicated in that it leaves it to someone else, something else, to keep track of where strings actually end. But like, that's it. And in fact, I brought these just to be sort of unduly dramatic. Like, all these weeks, we've had these sort of training wheels on, right? Like, where we've had these simplifications of CS50.h and strings existing, and now we're taking the training wheels off, because like, this is literally all that's been going on since week 1. I'm not sure that added anything. This is all that's been going on since week 1. But again, that's sort of the design of the course, is to help you understand first at a high level so you can just get things working and start playing around. Now we're taking a peek underneath the hood to see what really has been going on all of this time. And indeed, who cares what addresses these things live at? And so the way you would typically think about or draw this on a piece of paper is literally just with an arrow. S is pointing at a chunk of contiguous memory that is null terminated, so to speak. So where did string actually come from? Well, here's how I've been declaring strings today and prior. String S equals quote unquote high. String being supposedly the type of my variable. Well, it turns out that a string we have seen is really just an address. But it's the address of what? Just to be super clear. A string is really the address of its first character. So its first character. So its first char. So I think the implication of this now is that if we get rid of those training wheels and we get rid of even the CS50 library, we can actually start calling strings char stars. And this is what real geeks call strings. Like, oh, a char star in C is known to mean you're just talking about a string. But you're doing it as sort of a lower level actual vernacular, which implies that the address is, in fact, that of its first char. The last address of its last char is implicit in that null character that we've been using all of this time. So we've actually seen this kind of before. In fact, just recently we introduced the notion of persons, and I said, well, if we wanted to invent our own data type, and a person, for instance, would have a name and a number, we introduced syntax like this, which was kind of a mouthful, but the only interesting part is what's inside of the data structure in this case. Person was the name we gave to the data type. This whole struct is what we wanted a person to be, and the way we brought a person into existence in C was we defined a type using the typedef keyword in C. That's actually going to be the trick to what we've been doing in CS50 for the past few weeks. We're using typedef to define our own type. We want to create an alias, for instance, from one thing to another. So just to keep things simple at first, suppose that I'm really confused by int. Like, it's an integer, I get, but why int? Why int? Suppose I want to create a synonym called integer for ints. I could literally say typedef int integer semicolon. And this will bring into existence a data type called integer, which doesn't really solve a problem other than helping you remember that int is really just short for integer. But the syntax can be as simple as that. It doesn't need to be multiple lines with structures and person attributes like that. So accordingly, how can I define a data type for a string? I can say typedef char star, which is admittedly more mind-bending, but I want to think of it instead as a string. So inside of CS50.h, since week 1, has been literally this line of code. A bunch of other lines too, but this one-liner, because you're including it atop your code, brings into existence the keyword string, but it's just like doing an automatic find and replace between string and char star. That's all that's actually happening really underneath the hood. OK. What questions do you have on what a string actually is in this case?
All right. Hello, everybody. Thank you guys so much for joining me. Sorry if I am not answering all the questions right away. I just do pauses on these lectures at the points where they kind of naturally allow for pauses. I don't want to really break things up as people are watching them. I want to keep the flow going. So I'll pause it as he asks questions and stuff. But thank you guys so much for joining me here. Yeah, so this is how I found out CS50 string is just a char star. So when defining char star, do I need to put the star next to char here so it's not, enacted with this and kind of declared a pointer? Right. Like how do you not intertwine the two then, right? Because wouldn't that declare a pointer? Well, char star, I guess, is the pointer, right? You want to declare, oh, that's the whole point. You have a single char character. You are defining or declaring a pointer on this char character so that it goes to that location in memory and then does what? Why does the star do the iteration? That's my next question is, so all they did was typedef, as you can see in the lecture, all they did was typedef char string, right? So why does the pointer basically, unpack the entire string and iterate over it? Or are they doing something under the hood of the typedef struct? Are they saying typedef char star string and then inside of that saying, loop until you hit the null character and return back the hey Nate Programming, I appreciate you coming in and I appreciate you joining me and saying hello. You're awesome. Dabu, hey, I like that name, Dabu. Welcome, appreciate you coming in. Currently a CS major, freshman year of college. Awesome. Well, I'm a college graduate. I graduated back in 2021 with a degree in human biology and a minor in chemistry. I work as a formulation chemist for a biotech company where I make biological controls and various other products for their product line and catalog. And so I have been doing that since I graduated college, but I've been teaching myself Python and various now moving into more in-depth computer science topics for the past about half a year. We made a few projects from scratch on the channel live. We read books live on the channel from start to finish. We do a lot of practice problems and examples, and this is really about just taking our time going through this and really absorbing it and taking it all in. So yeah, that's my background, Nate Programming. Appreciate you coming in. Yeah, this is the EDX program for CS50X that is free to take online. There is a paid version, but please, please, in my opinion, just do the free one. There's no difference in content. It's just a paid for accreditation versus a non-paid for, and there's honestly no gain in the paid for version. It really does not have any sort of significance on your resume or abilities. Yeah, I have a degree in biology and chemistry. I'm not changing careers per se, but just taking on additional skills and continuing on with my education really and staying, I just find computer science really interesting and I want to learn more. Awesome. I appreciate you, Nate Programming. Thanks so much for joining me and following along. I have a Discord, you guys, where I've compiled all of my study resources from all of my notes that you see on the screen to all of my information about the lectures, all of my problem sets, everything. And it just breaks it all down into various threads in my Discord, link below. I also provide all the PDF versions of the books I'm reading live on stream. So it's really, I've been streaming every day for 2+ hours almost. At least in most cases. So yeah, I really appreciate you guys joining me. The star and char star s is part of the type a char pointer. So in my opinion, it's best written as char star s. So then in CS50 though, they just do typedef char star string. So why does char star do the iteration? Why wouldn't it just unpack the single character? Oh, well, because you're declaring char star on a multiple character quotation, right? So does it infer just in the language itself to go and until you hit the null character by this a string in memory, array in memory? The compiler assigns the char star to the first character in your string literally under the hood. Yeah, exactly. So if it assigns char star, but I'm declaring it to equal, because the char star is a pointer. Well, this as a pointer, right? S is technically a pointer then in memory to this first character. So what is doing the iteration under the hood to actually display all of the characters in the string? That's my question. When declaring a string in C with char star s equals quote high, is the s a pointer to the first char in the string? What is doing the iteration until reaching the null character? Yes, s is a pointer to the first character in the string quote high. The string itself is stored in a read-only section of memory in most compilers, and the s simply holds the memory address of the first character quote h. Okay. When iterating through the string, a loop typically increments the pointer s, or using indexing like s index I. The iteration continues until it reaches the null character 0, which marks the end of the string. Here, the pointer is accessed, and the current character in S++ moves a pointer until reaching, so you'd have to do the declaration yourself. So printf for example, will iterate the char until it finds a null character. So I don't have to do this declaration. This declaration is happening, this while loop is happening inside printf when detecting a char as its input. Or a char star as its input. In a function like printf, does the while loop until null character take place under the hood? Yes, some of the hood functions like printf use a similar loop to process strings until they reach the character. For example, printf of the string s, the %s format specifier tells printf to expect a pointer to a null terminated string. Internally, printf likely uses a loop like this. Okay, so it looks like CS50 with the has done some sugarcoating for us. We're going to have to start declaring pointers and using %s to actually do the iteration in printf if we wanted to print strings. Which I guess %s is no different than what we've been doing with using strings. So we've kind of gotten into the habit, but it's not actually printing a string. It's iterating over each character until reaching a null. Okay, interesting. So it's kind of crazy that even with a language where you have stuff under the hood, where you're accessing stuff under the hood, like because you're lower level than Python, there's still stuff under the hood. So look, a pointer is a variable the same way an int is a variable. What is a variable? A place a data stored. Yes, exactly. Int variable stores number, pointer variable stores memory address. Yeah, exactly. We're specifically talking about the actual inner workings, though, of these specific char pointers. Right? We know that this is a pointer to that first character h, but when called upon, I guess, with %s here, the %s in the printf has some sort of functionality to actually iterate over all of the individual characters until reaching null to resemble kind of a string. Aha. Cool. All right, I'm going to refill my drink. I'll be right back. Let me refill my drink. All right, got some cherry Coke. We're ready to go. It's cold in here. Get the heated blanket going. Get the heated blanket going. It's freezing. All right, thank you guys so much for joining me. We're watching Harvard CS50X 2025 Lecture 4 on memory. You can try printf of s with different formats to see different results you get. Oh, that'd be a good idea. We'll have to take a stab at that. Okay, let's keep going.
It's all what's inside of CS50.h. Yeah. Mm-hmm. A really good question here. Am I violating my own convention? I am not here. I do, Rongshin, do you know if this would work without the space here? We'll find out. He's checking. So this is a different context. I'm not actually declaring a variable here called string. I am declaring a type called string. It's possible it's allowed. I don't know offhand. So good question. Other questions? Yeah, and back. Really good question. When is it more useful to use char star instead of string? Honestly, after you exit CS50, you should not use string anymore. And in fact, among the things we're going to do next week is take the last of these training wheels off and take away the CS50 library so that you actually use only native C code per se, so that there are no more training wheels physically or virtually otherwise. So in the real world, if you ever write C, you would just use char star. We use string only because, I dare say, introducing char star and these memory addresses and like mailboxes all in the first week of C, it's just too much when all we want to get working is like Hello World or Mario or the like. Other questions? Yeah. Really good question. In my VS Code here, when I used the ampersand, I used it in front of each of the characters, 0 through 3, but I didn't use it here. A subtlety, but the reason I didn't use it here is because S, we now know, is already a pointer. It is a char star. So if it's already an address and %p expects an address, there's no reason to do ampersand S. It is already the address of a string. Specifically, I can now take away the CS50 library from my own code. Let me clear my terminal, go back up here, take the CS50 library away, which was a bad thing earlier. But if I now call this char star S, this declaration here makes more explicit that S is the address of a char. So %p expects an address. You can literally slot in S right there. But S bracket 0, S bracket 1, S bracket 2, those are actually chars inside of an array. So if you want the address of those characters, you do need to use the ampersand. And in answer to the question that came up over here, if I were to incorrectly use an ampersand here, that would be getting the address of the pointer, not the address of the string. But we're not here to talk about that today. Other questions? Yeah, in back. Where does %s come from? So that %s is supported by C and specifically printf. So strings exist as a concept in C. The word string does not exist. But when you use printf now, as I can here as another demonstration, I can do printf. I don't change this now to %c because I don't want to print a character. I still want to print a whole string conceptually. And I can pass in here s just as before. So printf has always understood %s. That's not a CS50 thing. The only thing that was a CS50 training wheel was the word string, which we can now take away safely. You just have to start writing char star instead. Other questions in back? A good question. So in your own code, should you now start doing typedef char star string semicolon so that you can still use string? Like, no. I mean, if after today or if after a few days from today you sort of understand what's really going on and you're comfortable with it, there's no reason to like keep putting the training wheels back on yourself in perpetuity. The simpler approach would be just keep using CS50's library for some amount of time, and that too is fine. Even come final projects, it's fine to still use these training wheels. The goal of today and next week and beyond is really to make sure you understand how you can write code successfully even without those same training wheels on. All right, so let's poke around just a little bit more with these capabilities. In VS Code here, let me propose that we can dabble a little further as by doing something like this. If I go into, let's say, addresses.c one final time, I'm still going to create s as quote unquote hi in all caps. But now, just to be clear, let's print out this string manually, just as we could have back in week 1, except now there is no string, there's only char star. So I'm going to do %c \n quote unquote comma s bracket 0. And then just for the sake of discussion, let me just copy paste this twice so as to print out these two characters. Again, I'm just playing around. In the real world, I should really use a for loop or something like that. But I just want to manually poke around with this new syntax. So let me make addresses again, /addresses, and I should see HI !1 per line. So that's just week 1 stuff. But now, let me propose that there's this other feature of C we can avail ourselves are, known lastly as pointer arithmetic. So if every chunk of memory has an address, and that address is just a number, whether it's in hexadecimal, decimal, binary, whatever, they're just numbers, I can actually do math on addresses. And if I can start in one location, I can go 1 byte away, 2 bytes away, 3 bytes away, just by adding 1 or 2 or 3. It stands to reason. So what's the implication of this? Well, it turns out that I don't need to use square bracket notation anymore if I don't want to. We introduced it in week 2. It is a feature of C, and it is a very, very common and useful convention, and probably the convention to keep using. But strictly speaking, we don't need to use square brackets anymore to print out individual elements of an array. For instance, I could change this first line to not be s bracket 0, but I can just say go to the first character of s. Because if s is a string, otherwise now known as a char star, and char star just means the address of a char, well, if I want to print out the actual char, I can use star s to go to that address, and where I will find, X marks the spot, a char in the computer's memory. But here's where the arithmetic comes in. Let me do another line. Printf %c \n, comma, go to s plus 1. So I can literally do a bit of math on my pointer to go one location to the right. I can do this once more. Printf %c \n, comma, star s plus 2 to go 2 locations to the right. And I'm doing this only because I know HI exclamation point gives me 3 locations in total. But if I now do again make addresses, /addresses, I get the exact same behavior. And in fact, the square brackets we introduced in week 2, which again come with C, is just syntactic sugar, so to speak, which is a term of art in computing, which just is a more user-friendly way of expressing this weirder syntax. The square brackets by the compiler are essentially converted into pointer arithmetic for me so that I don't have to write code that admittedly on the screen looks more cryptic than it would with just the simpler, more user-friendly square brackets. But all that those square brackets are doing underneath the hood is effectively pointer arithmetic for you. So if I want to play around one final way with all of this same code, I can even do things that probably aren't the best idea, but do speak to the power of this syntax and this language C. For instance, if I want to print out the actual string s, we know I can do this already, %s, and print out s itself, because s is a string, otherwise known as a char star. So make addresses just gives me high exclamation point. But what if I only want to print out part of the string? I could start partway in the middle of this thing. What if I do this? Printf %s \n s plus 1. So no star. I don't want to print out a char. I want to print out a whole string. What is a string? A string is an address of the first character of the string, still null terminated. So when I compile this code, printing out, and actually let me get rid of the previous line. When I compile this code with make addresses and I run /addresses, what should I see on the screen now? If I'm not printing starting at s, I'm printing starting at s plus 1.
You should just see I.
Yeah, I think you're saying I, like I exclamation point y, because if these strings start at 0x123 and go 0x124, 0x125, 0x126, and I'm starting at 0x123 plus 1, that means start at the second character, and I think, yep, I now see I exclamation point. If I change it to 2, I now see, after doing make addresses, I think I should just see very excitedly an exclamation point, and that's it. I probably don't want to go even further than this, because then who knows what's going to happen if I start printing beyond the boundaries of the actual string. And that, in fact, is going to be one of the trade-offs here. Even though now, with these simple operators like star and ampersand, we can now manipulate and understand memory at this lower level, we can actually do a lot of damage. And among the things we'll talk about today, too, after the break, is recall the CrowdStrike fiasco a few months back, where like systems around the world broke down, including airlines and the like. That stupid, stupid issue was the result of such a simple problem that, after today's break, you too will understand. But in the meantime, in happier news, let's have some little bites of blueberry muffins in the transfer.
I wish I had some of those.
See you in 10.
All right, woohoo!
Don't applaud, we're not done. See you in 10.
All right, awesome. We'll take a little break here and we will answer some stuff in the chat. When doing char star, you're opening a memory cell to hold each character. The pointer variable holds the memory address of the first char, yeah. When you use printf %s, computer knows when to stop when it reaches the last char. You could do the same manually if you want to make a loop for print for each with print %c. Yeah, exactly. So if you do the %c, you would just get the first character. Like in that case, you could do, %c of the string plus of the s+1 to access the actual first character or the second character or the I in high, and just print out that one alone. But because you have the %s there, the %s in the printf functionality will go ahead and iterate through the entire string until you reach the null terminated character. So awesome. I thought that this was going to be a little bit more like tricky, but I'm kind of getting it so far. So not too bad. Now hope. Whoa. We're not gonna get too ahead of ourselves. We gotta obviously practice a little bit, but I do kind of understand at least what's going on with here with charge, and I can kind of see now we're kind of pointing to and alluding to like slicing, right? This is a way of kind of taking slices in a way. Now, how would it take reverse slices? I'm not sure. Maybe until you have to reach until you reach out. You probably have to go until you reach the pointer. Like if you take a reverse slice or something like that. So because you have kind of like it's kind of like a linked list almost in a way where your pointer is your head and it stays there, and then you're null terminated, and you can bounce back and forth kind of with a was it a doubly linked list? Yeah, it was a doubly linked list that had sentinels on either end that we learned about in our data structures and algorithms reading. So we're putting this together, everybody. Woo! It's interesting. Hey Pablo, what's your current study plan? Well, you're looking at it, my friend. We're doing various courses, Harvard CS50X, but I mainly do a lot of reading out of individual textbooks like Python Crash Course and data structures and algorithms in Python like you see here. So if you want access to any of the books you see on my screen, feel free to join my Discord link below where I compiled all them into like a roadmap, and a lot of other people have also provided their resources. But yeah, this is the study plan. Winghong, what do you do if your last character is %0, or what the delimiter is for the last character? Say I want to write high %0 and C ends with %0, so I want to save high. You mean \0? I don't think %0 is the right context, but I get what you're trying to say. Like if you wanted to directly say \0, you might have to escape the \0 somehow. So I know you're escaping the escape, but that's probably what you'd have to do. Like if you do print statements, like in at least Python, and you want to actually display a \, you have to escape the \. Nate, programming, you learn fast. Thank you so much. I appreciate those kind words. It took me a long time to understand this. Well, I just going to show you guys that the hard work is paying off here. We've been coming in, showing up every single day. It really is almost as trivial as just kind of showing up every single day. Now, I will say it gets to a point where you do have to apply some effort into these things. It's not linear to the amount of time you put in, but at the start, just the amount of time you put in goes a long way. Now, you'll reach a certain plateau where you really have to start applying effort to maintain that linearity with the time versus learning, right? But or learning gained. But at least at the start, just by showing up and actually participating and paying attention, you can pick up quite a bit. And so especially if you do that every single day, right, and compound it on each other. Now, if I will say, like, if I only did this 3 times a week, I'd probably be a lot slower. Like I just wouldn't be as fresh remembering concepts from the last study session. So there are trade-offs to these things where I have had to go every day to maintain this kind of level of success, I guess you could say, with picking up these concepts fairly quickly. But that has been at a cost, though, of just time spent and effort as well. Appreciate you guys coming in. We're learning CS50X right now. Awesome. All right, let's keep going.
All right. we are back in one erratum. So this was the line of code I proposed in CS50.h. It's not quite the line of code in CS50.h because, as was asked, stylistically, the quote-unquote right way to write this would indeed be without the space after the star. So even though string is not being declared as a variable here, but rather as a type stylistically, and I just asked style 50 for the correct answer, it would indeed omit the space. So this is what I should have said earlier, and we'll fix that in the online version thereof. But for now, let's actually transition to taking a look again at the computer's memory and revisit some problems that we looked at indirectly over the past couple of weeks and better understand why things worked and now work the way they do. So let me go over to VS Code here, and I've written in advance a relatively simple program. I'm still using CS50.h and standard.io.h for this example. I'm calling getIn twice to get two variables, I and j, so two numbers from the user. And I'm checking for equality using equals equals. So if I equals equals j, I'm going to print same. Otherwise, I'm going to print different. So fairly straightforward, and it should just work. Indeed, if I open up my terminal window and I do, if I open up my terminal window, do make compare, because this file is compare.c, I can then do /compare and type in two numbers like 50 and 50, and they're indeed the same. Or I can do it again, 50 and 51, and they're in fact different. And I'll stipulate that pretty sure this code is in fact correct. But what if we make a change of sorts and actually compare not integers but strings? What's going on? Well, let's first consider what is happening with integers. So here's my computer's memory, and I've zoomed out a bit just so we can fit more on the screen at once. And here might be where I and j end up in the computer's memory when running this program. I here, j here, both of them 4 bytes, because both I and j are integers. It stands to reason then when I compare I and j, we are literally comparing 50 against 50 in that first scenario. And indeed, it's technically 32 bits and 32 bits, but they're exactly the same if they're both storing and representing the value 50. All right, so fairly straightforward. But what about strings? In fact, we deliberately introduced strcmp, or for string comparison, because when I last tried to compare two strings, it didn't actually work as intended when using equals equals. So in fact, let me go back to my code here and close my terminal window and just make a couple of changes here. Same idea, but different data type. So let's do string s equals getString. And we'll prompt the user for string s now instead of I. Then maybe a string t, just to keep the variable name short for the sake of discussion, and prompt the user for t here. Then let me go ahead and say if s equals equals t, go ahead as before and print out same \n. Otherwise, go ahead in my else clause and print out quote unquote different. All right, so same logic, but different data types, using strings for the type and getString for the function. Let me open my terminal window again, make compare. No syntactic errors, but let me go ahead and do /compare and type in something like, how about hi and hi, both in all caps, but they appear to be different. I can try again, maybe my name, David and David, also different, even though it seems to be the same. So what's going on? Well, you might already have an intuition, and someone last time when we looked at a program like this did have an intuition, but what if we make it more explicit now? What if I change my strings to literally char stars, which doesn't affect the functionality, but takes off one of those training wheels? I'm not going to get rid of CS50.h altogether, because as we'll see, I still want to use getString. Otherwise, it's a pain in the neck in C to get user input, but we'll come back to that. But s now is not only a string, it's more precisely the address of a character, technically the first character of a string. So what then is being compared on line 9 that's yielding this different answer? Why are hi and why are David different, even if typed identically?
They're in different places in memory.
Yeah, it's two different addresses. What's really going on, if we take a look at the computer's memory now, dealing with strings, is the following. Here's that grid of memory. Maybe s ends up here, and maybe the actual array of characters ends up here. Because notice, when we're using strings, technically, we're storing the address, and we're storing the actual characters. And that's all been happening magically in one step for us, one line of code. But technically, there's different chunks of memory involved. And it might be at 0x123, 0x124, 0x125, and 0x126. All of that happens automatically with that one line of code when I create and initialize s. Meanwhile, s is going to therefore store the address of that first character, hence the whole idea of a char star. But what is t? Well, maybe t ends up over here, somewhere in memory. Maybe the other hi that I typed in, or a bit later, the David that I typed in, ends up at maybe 0x456, 0x457, 0x458, 0x459. Again, who cares what the addresses are, but they are back to back to back, which is important. But suffice it to say, then, what ends up in t is the address of that second string that I actually typed in. And for all intents and purposes, that's like s pointing to this chunk of memory, t pointing to this chunk of memory. So when I use literally equals equals to compare the two strings, that is, compare the two char stars, that is, compare the two addresses, clearly they're in different places. It's like asking the computer, are 0x123 and 0x456 the same? Well, of course not. Those are literally two different numbers, written in hexadecimal or anything else. So we needed a solution for this, and that is why we introduced strcmp, the function that actually addressed this properly. If I go back then to VS Code here, and instead of using equals equals, I give myself access to our old friend now, the string.h header file. In that library is the definition, the declaration of strcmp. So I can do strcmp passing in two variables, s, comma, t. And recall, what is the return value I care about? What does strcmp return if two strings are equal? So it returns 0. Otherwise, it's a positive or a negative number, which helps with alphabetization. But that's not what we want here. I want to make sure that the return value of strcmp equals 0. And what does that do for me? Well, if I open up my terminal again, make compare, /compare, and again type in hi, exclamation point, enter, and hi, exclamation point, enter, now they're in fact the same. But if I type something different, like hi and bye, those, of course, are different, not on the basis of their addresses, but on the basis of their actual characters. And in fact, that's what's really happening. The way strcmp is implemented by someone else years ago is that they have some code, some kind of loop probably, that first dereferences s and t respectively, goes there, and then in some kind of loop iterates over these two strings in memory, checking whether the individual chars equals each other,
exactly
stopping
what
once
we
it hits
said.
/0 in either
exactly
string.
what I said.
And if they happen to look the exact same character by character, then it returns 0. It's a little fancier than that because it uses some less than or greater than to figure out if one comes before the other ASCII-betically. But it is doing the walking across this string. So the person that implemented strcmp uses a for loop, a while loop, whatever, to do all that legwork for us. Questions on strcmp or what we've just revealed? Yeah?
Oh my gosh, pause. All right, cool. Hey, Levi, thanks so much for coming in. I appreciate you joining me today. Sorry I couldn't get to your question sooner. I just paused at, places where he kind of allows for pauses to help not break up the flow of the lecture in case other people are watching. But yeah, we're watching week 4 on memory right now. We've completed all the way up to this point in January so far, so we're a little bit ahead of schedule, which is really awesome. Yeah, and I just kind of do this to also help break up some of the monotonity. Is that the right word? I'm not or whatever of the of just the other content like reading and Python. I think a lot of people really enjoy the Python content and everything, but after doing it like 5 days in a row, it's nice to take one day to do a little bit of C and learn a little bit deeper down into the under the hood of Python and what's going on, and get some practice with that as well. So we're definitely not giving up on that for sure. Python is our bread and butter on this channel so far, but we're got to expand into some other realms at some point. So we're just getting some little tasters here. No worry, Levi. I appreciate you. Nate Programming, I think I remember coming to your live last year. Yeah, I think your name was quite familiar. You've come a long way. Congrats. Thank you so much, dude. I should learn biology and chem like you. Honestly, just stay with CS. I think you're probably really good with CS. You make plenty of good money in there. Biology, it's rewarding, it's fun in chemistry, but there's just not as much lucratation. I'm struggling with my words today, but it's a lot slower paced. I mean, it's fun, it's great, but when you're dealing with FDA stuff, it's all regulated, and it's it's kind of crazy. But yeah, Yeah, thanks you so much for those kind words, and yeah, follow along so we can connect in the future and keep interacting and networking together. I really appreciate you coming in, Nate, and joining. Once again, we meet again. Hey Pepe, what's going on? Did you have any experience in CS before starting this? No, I had zero experience before starting this, channel 6 months ago. So I started with Harvard CS50P, and I really struggled through that course. It was, a beginner course, but I had never seen any code before, or written, read, or anything, and so I barely even knew what Morse code was. So that was definitely a learning curve that we had to get over. But once we have crossed that hurdle, we're kind of on our way, and we're ready to continue taking on. Things are obviously going to get harder and everything, but we've set ourselves up quite nicely by understanding the basics before moving on to harder things. And so it's just kind of going that this method is kind of, I guess, working for the most part. Thank you so much for coming in. If that sounds like something you're interested in, consider following along. I stream every single day. At least I try my best to, even if I struggle, have a rough day at work or whatever. I come in and like to hang out with you guys and learn and just keep compounding this material every day. I'm really dedicated to learning this, and I really find it passionate. I really find it interesting, and I have a passion for it. Yeah, Levi, I agreed. It's great to look under the hood. Yeah. So this is actually giving me a lot of insight on what's going on behind Python as well. So this is not only helping me learn other things, but also helping me become a better Python programmer, because I can understand those function time complexities better, because I can see what's going on under the hood with declarations of like string and string comparisons, because it's not all as fast as we think it is. Awesome, Levi. Congrats to you, my friend. Let's give 5 big booms to Levi. Boom, boom. I love those Costco guys. All right, let's keep on moving here, you guys.
Good question. Is it subtracting the ASCII values of the characters? Not necessarily. It's probably comparing them with less than or greater than literally, because if you're comparing A and B, that would be like comparing 65 and 66 if capitalized. So you don't need to subtract anything per se. You can just compare the magnitude of those values. Yeah? A good question. Do we use 2 locations in memory for both the pointer S and the actual array of characters? Short answer, yes. And how that is happening is as follows. If I go back to VS Code and highlight the lines of code that we just wrote, for instance, line 7, the left-hand side of the expression here creates those 8 bytes in memory called S that will eventually store an address of the first character of some string. The getString function written by CS50 handles the process of allocating the array for H, I, exclamation point, and the \0 and puts it somewhere. I depicted it down here on the screen. So getString allocates one chunk, and your code here allocates the other chunk. There are other ways to do this. And in fact, once we completely take away the CS50 library, you have to allocate not only the left side, but also the memory for the right side of this expression, so to speak. And we can do that in different ways. And we'll come back to that soon. All right, so if we now know and appreciate that these 2 addresses are indeed different, S and T, it turns out we can kind of play around with, create some new problems, but also solve them as well. So how might I go about, for instance, let's see, seeing what we just did. If I go back into VS Code here, let me just do something simple and no longer compare these, but just to make the point using our %p format code now, I can actually print out the actual values of S and P if I want to S and T if I want to convince myself of all of this. So I can print out, with %p with the value of S, with %p the value of T. And in this case, even if I type the same thing, watch again what happens. Make compare, /compare. I'll type in hi, and I should now see 2 addresses. But per the depiction on the screen, they do end up in different locations. They're similar locations. These numbers are actually pretty similar, but notice they differ down here. A B and an F puts them a few bytes apart. So they're actually next to each other in memory, but they're not, in fact, at the same location. So that's what's happening underneath the hood. And just to be super clear, it is rare, if ever, that you as a programmer will ever bother using %p to print out an address. Generally, we do not care where things are, just using it for the sake of demonstration to make clear that we could go there if we so want. All right, well, what if we want to make maybe manipulate these strings and actually change them in some ways? Let me do this. Let me clear my terminal, close compare.c, open up a new file called copy.c, whereby I might ultimately need to make copies of strings in memory. And let me go ahead and do this. Let me include cs50.h, so I can still use getString. Let me include, how about standardIO.h, as we often do. Let me include string.h, as we now do. Int main void for my main function, and then in here, let's do the same thing as before. String s equals getString, and prompt the user for that string. Then let's go ahead and copy the string as follows. String t equals s. Then let's go ahead and capitalize the first letter of this string. And it might be a little hazy, but we introduced a library a couple weeks back called ctype.h, which has a bunch of functions related to types in C, one of whose functions, recall, is toUpper, which just uppercases a character. So what I'm going to do here is I'm going to change the first character of t, but not s, to equal whatever the return value of toUpper is, passing in the first character of t. So I'm just changing the first character of t to be the uppercase version thereof. Now I'm going to go ahead and print out the value of s is %s\n. I'm going to plug in s. And then I'm going to do the exact same thing for t, so I can see both the before and the after version of my capitalized change. Let me open my terminal. Let me do make copy. And I screwed up because I should be including not a C file, but a header file. So ctype.h at the top. Unintended mistake. Make copy again. That worked. /copy. And now this time, let me deliberately type it in all lowercase, HI exclamation point, because the whole point of t is to be uppercase. If I hit enter now, I see, a curiosity. Both s and t were somehow capitalized for some reason, even though I only changed on line 12 the first character of t. Why might that be?
My initial assumption is that because we have declared string t equal to s in memory, it is also at that location in memory. In Python, we would create like a new variable in memory, but in C, it's just referencing that same place in memory as a new alias called t. And so whatever you do to s will also be done to t and vice versa. That's my assumption. Hello, the croissant. Hello, welcome. I appreciate you coming in. That was a pretty good French little roll there. I appreciate you're quite new to CS, kind of like me. I'm not a CS student in physics undergrad. I've just gotten into programming recently because I found it kind of fun. Well, awesome. That's really, really fascinating news. And physics is really cool for programming. There's a lot you can do there math-wise. And so you might find yourself having a lot of tools at your disposal to be able to kind of recreate a lot of those math, physics like things you might have learned in your undergrad. So really, really awesome that you were able to jump in and find the channel here. Appreciate you joining. Leon Bryan, hey, thanks for coming in. Yeah, no problem, Levi. Congrats on that. Yeah, Nate programming, exactly. Well, don't be afraid of math. We're going to be getting into some math shortly on the channel soon. I think when we complete this course, we're going to start up a math course actually for reviewing our calculus. We'll probably start up at Calculus 1 again. I've already completed Calculus 1, but that was a long time ago in college, so we're going to need some refreshers. So we'll go through calculus and get deeper into math on the channel. So if you're wanting to do that alongside me, then join along here. Yeah, point to the same address. Isn't it the same in Python? It might be, Mahan, now that you think of it. Yeah, actually, it is the same in Python. If you give it an alias, it's the same in Python. Yeah, you're right. I misspoke. I'm sorry. What kind of math is basically needed for CS? Algebra, calc, statistics. Isn't it Python the same? Yeah, and a little geometry. You don't need to know anything advanced for basic CS, but if you want to get into graphics, programming, or machine learning, linear algebra and stuff is needed. Hey, Brian, welcome. Appreciate you coming in. Hopefully I'm pronouncing that right all this time. Thank you for jumping in with me and joining back. You got to be great at math, being a chemist. Please, that's what I need help with most. Yeah, I was pretty decent at math. In college, I took like a flipped course in my calculus where we self-taught ourselves. So I guess that's why I kind of have some experience being able to self-teach myself. This is I was kind of had to force myself that skill to learn that skill to be able to succeed and actually pass with a really good grade, an A in my calculus class, my freshman year of college. Um, so I just remember being in the math lab, the learning center, and the math center at my college every single day working with the graduate math students on problems. I remember that there's this one problem in calculus where you had a leaning ladder against a wall and it slowly fell, and you had to calculate something. Like I don't know if it was the time or what it took to fall, but it was a problem of a ladder against a wall, and it was something like that. And I remember struggling with that problem forever back in college. But yeah, we're gonna be diving in. I was decent at math. I was able to do it pretty well, but honestly, guys, I have forgotten a lot of my math. When we were going over the DSA in Python, I really had to kind of refresh my memory on our logs and exponents. I just don't use that a lot anymore since graduating college. When you graduate college in a physical science field, you realize that you kind of are just a cog in the wheel to make products for companies. You're no longer, unless you're doing like R&D or analytical things or like research and stuff, you're kind of just a product maker at that point. And so you make chemical products that get sold to make money for the company, basically. So at least in my specific field, I just kind of don't use a lot of that math anymore for chemistry. And so it's more just physical chemistry, actually doing the experiments and doing the formulation in my manufacturing, rather than the actual like the maths behind it. But pardon me, I really would like to get into that for sure. Quinn, hey, welcome. Quinn, I appreciate you joining me. Do you think it's worth the time to do projects that come with the Harvard lectures? What do you mean the projects, like the problem sets? If you're talking about the problem sets, yes, um, I highly suggest that you do the problem sets at the end of lectures to help reinforce what the lectures talked about. Now, I will say the problem sets are quite challenging for most people when coming from the lectures for the first time. Now, I'm not trying, this is not a gloat or anything. I was able to kind of get through them fairly quickly because we've had experience with Harvard's format before in CS50P and with all of our other practice. But some of these problems that I recently did in the last week, like Tideman and the runoff problem, were pretty challenging. The Tideman one, I had to get a lot of help from AI and get resources from you guys as well. But so that one was pretty tricky. But if you're talking about projects, I honestly, guys, I know people really ask this question a lot, and I kind of go over it a lot. But I highly, highly recommend just grinding through projects on your own, like, and really not trying to watch um, tutorials on projects. Now, it's great to watch tutorials to get familiar with syntax, in my opinion, but I have not watched tutorials to build projects. All my projects are 100% from scratch, my own idea, my own way of thinking. And because I went through that struggle of having to come up with an idea, figure out how to put it into words and code, figure out how to manage the data of it, how to manage the user inputs. My projects aren't that elaborate in terms of their functionality. They're just a simple task tracker, inventory system, and now a small business manager for managing expenses, sales, and inventory all together, and generating business information. But it just utilizes basic Python functionality, but just compounded in a way to create a cool idea and bring it to life. I'm not reinventing any wheel. I'm not creating something that's going to save someone's life or make them millions of dollars. No, I'm doing this for the sole purpose of just trying to learn, which is the value in itself. So the project serves that purpose. And proofs. Yeah, we need help with proofs too, for sure, Mahan. Proofs. For those that don't know, I posted one lecture of the MIT discrete mathematics course, and I started to watch the second lecture, and I was like, I'm not doing this yet. I gotta get some prep work done. It got way too deep really fast. It's pronounced like Brian. Okay, my bad. I've been saying Brian this whole time. Brian. It's like fancy. Um, Could I get you to talk to my nephew? He will not take school seriously and is so bright. Yeah, throw him in the stream. I, I people have told me I tend to rub off and give people a positive light, but honestly, it's hard when you're a kid. You just don't have that full 360 view perspective of what life's really about at the end of the day. You just kind of have that sheltered view of really what I want right now, which is hard to kind of convey to kids at times. Hey Harry, welcome. The ladder calc problem is an optimization problem. Okay, so someone remembers what I'm talking about. Someone remembers what I'm talking about. That ladder against the wall that like slid down or something. I remember my freshman year of college, like 5 years. No, it's more than that. It was back in 2018, 2019, yeah, something like that. So a long time, like over 5, 6 years ago, I remember that problem. It stuck with me this whole time. That's how much I hated it. Does anybody else remember that problem besides Harry? I didn't really pay attention in high school. Am I going to struggle with CS? No, I honestly think it's up to you, man. It's up to how much effort you're willing to put into it. If you really dedicate yourself, you got to think of it like this, guys. You might be discouraged, like, oh, I don't want to I'm not going to be as good as this other person. But if you realistically think about it, that other person is just a human being. That other person that whatever, Nate programming in the chat, he's a human being. He knows what he's talking about. He's a CS graduate right now and he's given some advice. Nate's a human being. What he's done is attainable in terms of the capabilities of other human beings. So in my opinion, if some other human has done it with enough effort, energy, and passion, I too can do that. Now, if some things are against my abilities, like jumping, really high, and yes, I could dunk a basketball in high school, but could I do it now? Probably not. If I worked really hard to, maybe I could do it. Probably couldn't though, because I just can't jump super high anymore. But you're kind of limited by physical things. But in terms of like mental and you would be surprised just how far you would get with just passion and drive. Think about it like that. Like people are people, and if someone else has done it, then you can too. It's doable. It's proven, right? Math is not hard. The different ways of counting and summation. You got this. You probably would be a good role model. I remember the problem. The related rates problem. I had to look it up again. It's been 10 plus years since college. Man, other people got the same exact problem. Man, everybody had the textbook. It was like orange or something. I took pre-calc in high school and we had the ladder. It's been 7 years. W mentality. Yeah, Inferno, right? If someone else has done it, why can't I, right? Why can't you? It's really just you telling yourself that you can't. Yeah, I started with the Harvard CS50P course. If you're trying to learn programming syntax, I highly recommend just taking a stride at first at the Harvard CS50P. That just Python really helps you get familiar with basic syntax because it's just very intuitive for the English language and doesn't really have a lot of crypticness to it compared to like this. It does have cryptic syntax in certain ways, but it's a lot more understandable and straightforward with just basic keywords and type. There's no type declarations or things like that. So it's a great way to get familiar with the syntax, and then I would suggest doing CS50P and then doing this one on top of it like I'm doing afterwards to help dig deeper. All right. If we don't keep going here, guys, we're going to be here all daggum night, so we got to keep going. What is the hardest math class you've taken? Yeah, so to be honest, you guys, biology didn't require too deep of math. Biology and chemistry, like yes, I had to go up to calculus, but my hardest classes in college were like my anatomy classes or my like advanced chemistry classes, where like I wasn't really doing difficult math per se, but I was solving difficult like chemistry problems, like modeling, reactions and predicting reactions based off of, or what type of elements and what type of solvents you might have in certain forms. So it was a completely different way of thinking, not ways of, piecing together math, but piecing together actual physical items and elements in the real world. So it was a different way. It was hard and challenging itself, but my anatomy class was really difficult too. Like my human phys class, like that one had like a 50% like drop rate almost within the first week. So it was pretty tough. But we got through that one. Sorry, we are stopping. We're not getting too far. We got a lot of chats here. I like talking with you guys. So the hardest math class I've taken was probably up to Calc 1, but I did take my junior level of college. I had to take a Statistics for Scientists class. Statistics for Scientists class. It was a 3,000 level statistics course. I think it was like 3360 or 3630. And that one where you talk about significant p-values, alpha values, you really go over like the in-depths of the normal curve and the bell curves. You do a lot about in-depth, like really in-depth probabilities. But I'm gonna be real with you guys. After that class, a lot of that information, because it was, I was like, I'm moving on, right? But I was young back then. Looking back, I wish I would have kind of compounded that better. Or investing more time into others you love rather than yourself. Or investing more time in others you love rather than yourself. I'm not sure what you're talking about, Levi, but sounds like a great note. For learning syntax in a language to language, the bro code long videos will help, I think. Yeah, those ones are good too. Calculus 2's destroyed me, but it had a good lot going at that time. But I had a lot going on, yeah. Organic chemistry, yeah. Leaving you with not much time, energy, and concentration left with your study is the attention you should. I guess the thing is going to go for tomorrow. You can finish the lecture by the end of the day. Yeah, right. We'll have to, this lecture's taking a while.
Why might that be? Let me offer a bit of a hint. What if, again, we take off some of these training wheels? S is just a char star as of today. T is just a char star after today. So what's happening such that I'm seeing that
they're at the same place in memory? Come on, Harvard students. Why aren't you getting this? I got this. Come on.
Change affect both
Put
S
me in Harvard.
and T. Yeah.
Come on.
Yeah, I'm really copying literally S and T, which means both of those variables contain the same address. So even though I'm following T's address, that leads me to the same location that S is pointing to. So I'm essentially changing the one and only one copy of high exclamation point. In fact, we can see that as follows. If I open up my computer's memory, let me propose that S ends up over here. Maybe high and lowercase ends up down here, maybe at those same addresses as before, OX123. Therefore, S contains OX123. Meanwhile, T is a separate variable that I declared with almost identical code, but I then set it equal to S, which is like literally copying the value in S into T. If we now get rid of all these unnecessary addresses and just use abstraction, it's as though S and T are pointing at the same place. So it doesn't matter whether you follow S or you follow T. When you dereference either, as is implied by the square bracket notation, means go there, you're just changing the one and only copy of H. And so whether you print S or T, you print out the capitalized version thereof. So what's the solution here? Well, we actually need to be a little more clever when it comes to making actual copies. Up until now, super simple to copy integers, chars, floats, longs, doubles, all of those primitive data types, super simple because code like that on line 10 would just work. But whenever you're talking about something fancier like a string, which isn't one location, it's sort of a sequence of locations, someone's got to do the hard work of allocating another chunk of memory, copying the characters from old into new, and somehow keeping track of all of that. Now, we'll do this ourselves in just a moment, but thankfully, there's going to be a library that can make our lives easier instead. So let me go ahead and do this. Let me propose that we, in VS Code, improve this code as follows. Instead of just blindly copying S and calling it T, I'm going to actually use a new function called malloc. We haven't needed this before. It's among the remaining tools in our toolkit in C, but malloc stands for memory allocation, and it's a function that super simply lets you pass in as input a number. How many bytes of memory do you want? and it will hand you back a chunk of memory. Specifically, it will hand you back the address of that chunk of memory. Specifically, the address of the first byte of that chunk of memory. Free is the opposite. Once you're done with this memory, you can call free and give it back to the computer so that you don't eventually run out of memory. You can give things back when you're done. So how can I now leverage this in my own code? Well, let me propose that I implement a copy a little more cleverly here. Let me go back to VS Code here, and instead of using s equals t, let me instead say t initially should store the address of a new chunk of memory that's big enough to store the characters of s. The way I do that would be malloc, and how many do I need? hi exclamation point and the null character. I could just get away with saying 4. Give me 4 bytes of memory and store the address of the first byte in t. That is what line 10 is now doing. Now, that's kind of a stupid approach. Like, I shouldn't hard code the number 4, because who knows what the human's going to type in. But we have other friends here. We can say, figure out what the length of s is, add 1 more byte for the null character, and ask malloc for that many bytes. Because now, no matter how big or small s is, we're going to ask for the appropriate number of bytes. What is stored in t at this point in the story is the address of that chunk of memory. Specifically, the address of the first byte in that memory. Now, there's no null terminator or anything. Everything in there at the moment is sort of garbage value, so to speak, until I put something there. So what I'm going to do now is this. After I allocate that chunk of memory, I'm going to use a for loop, just like the authors of strcmp had, but for a different purpose. For int I equals 0, n equals the string length of s, semicolon. And we've seen that technique before, so we don't waste time calling strling again and again and again. I is less than n, and then I plus plus. And inside of my loop, I'm going to copy into location I of t, whatever's at location I of s, effectively copying from left to right all of the characters of s into t.
Yep.
At the very end of this, I could do something, but I think I could do something to manually add a null character to the end of my new string t, but I don't think I have to do that. The one time this makes sense is perhaps now. I'm going to actually iterate from I less than or equal to n, because I actually want to copy the null character as well. So if the string is hi exclamation point new line, I actually do want to go from 0 to 1 to 2 to 3 and then stop. Normally, I would go from 0 to 1 to 2, but I want to include this sort of secret null character there. So I think this for loop will capture that for me. I'm not going to change any of the rest of code. So all I have done that's different now is explicitly allocate a new chunk of memory for t and copy everything in s into t. But to use malloc, I need a new library. I'm going to go up here and include standardlib.h. And again, you learn through practice what's in what library, or you can go to manual.cs50.io and just look it up to figure out where, in which header file something is. And I'm also going to include the same header files as before. So the only change is to add standardlib. Let me open my terminal window, make copy, /copy, and now let me type in hi exclamation point in all lowercase, and I should see in a moment the output of both s and t, but hopefully only one of them is capitalized t. And indeed, I've done it somehow. So what actually just happened? Well, if we actually go over to a visualization thereof, here is my computer's memory when s exists. If, though, I'm going to allocate new memory with malloc, that's like calling malloc, getting some chunk of memory. Maybe it ends up here. Maybe it ends up somewhere else. I'm just keeping it in the same place for discussion. And the first address happens to be 0x456. Well, what gets stored in t? The return value of malloc. And malloc returns the address of the first byte of memory. So what ends up in t is effectively 0x456. But who cares? We'll just draw it abstractly as an arrow. What does my for loop then do? Well, it iterates over s and t in lockstep, such that the h gets copied, the I gets copied, the exclamation point gets copied, and because I use less than or equal to, we also copy the secret null character as well. Then I use toUpper on t bracket 0. Here's t bracket 0, and so I think only the H in T is now capitalized. It's not a particularly interesting exercise, but it does demonstrate really with as few steps as possible how we can solve this problem of actually copying strings in memory by allocating enough space for them in that actual memory. But there is a caveat. A lot of things, unfortunately, this week onward can go wrong when it comes to memory. Like your computer could be out. Maybe you have an older computer. Maybe you have a really fancy program that has so many variables, so many arrays, that eventually you run out of memory. It's possible that malloc can fail. Something can go wrong, and malloc will not, in fact, return to you the address of the first byte of memory available, because if none's available, it's got to return something else. So in cases of error, what malloc really returns to you is 0. Like, I have no valid bytes for you. And 0 itself is a number, so that's a little confusing. And this doesn't really help with confusion. What malloc returns if an error happens is null with 2 L's. This was a stupid design decision decades ago to call the character 0 NUL and the pointer 0 NULL, but this is where we're at. So NULL is the address 0, and it almost always signifies something went wrong. We just need a special symbol to signify something went wrong when returning a value from malloc. So how can I use this? Unfortunately, now, just like in some of the problem sets thus far, when you've started to add error checking to when things can potentially go wrong, your code gets a little more verbose. But what I'm going to do here, if I go back to VS Code, is the following. What can go wrong? Well, if T ends up equaling null, that is, if it has a bogus return value in it that is not a valid memory address, then there's not much I really can do except like return 1 just to signify error. I could print out an error to the screen. I could inform the user somehow. But if malloc returns null, I had better not proceed to try copying things from left to right into it, because there is no memory there. That chunk of memory on the screen at bottom right does not exist if malloc fails, of course. So you don't want to go there and start blindly touching memory, let alone capitalizing memory that's there. So I have to start adding in some of these error checks in this case. And in fact, even this is a little naive. It's probably not safe to even assume that the user typed in any string at all. Maybe the human, just to be difficult or making a mistake, and just hit enter. So the length of the string is 0. You probably shouldn't try capitalizing 0 either. And so what we should probably do down here, too, to be super safe, is only if the str length of T is at least greater than 0, then go ahead and capitalize it. Otherwise, do not touch that memory either. In other words, starting this week and next week, and even when we get to Python, you should start acquiring an instinct to code defensively. Things can go wrong in your code, in someone else's code, and if you do not handle those situations with ifs or else ifs or the like, your computer will crash, the thing will freeze, or the like. And again, to tease the CrowdStrike example, if you screw up and you don't check the boundaries of something, the length of something, who knows what can happen? Because if you touch memory that does not belong to you, the typical behavior, again, is to crash, to freeze, to do some undefined behavior like that. Now, I will say, this is getting really annoying. I mean, I've written, what, like 30 some odd lines of code just to copy 2 strings. That's a little unfortunate when this is probably a pretty common thing to do in the real world. So it turns out there are library functions like this, too. And in fact, I can get rid of a lot of my code here for copying. And I can actually just call a function, strcpy, strcpy for short, and pass in the destination, pass in the source, semicolon, and that will do all of the for loop or the while loop or however that person implemented it of copying one into the other. The ordering is a little weird. It is indeed destination, comma, source, but that saves me the trouble of doing all of that code myself. Questions then on what we've done here, the key details really being malloc and one omitted detail, which we'll come back to. Yeah?
So I want to go back here and talk about his code. Wouldn't it be more efficient to, instead of declaring if str length T greater than 0, to do the is upper, right? Before you call the copy, what if you check if the str length is equal to 0 at T? Don't even do this malloc thing. Just if it's 0, right, then you can just create a new area of memory that is blank, right? And return that functionality. So then you wouldn't even need to do this declaration here, because you know that if you have memory location, then you can do the thing. What do you guys think about that? Hey, Arrow, welcome in. I appreciate you joining me here. Sorry I didn't get to your chat sooner. I'm just only paused at the appropriate points here to keep the flow going. Um, um, hey, Michael, what do you do when you burn out mentally? um, uh, well, to be honest, since I've gotten out of school, I kind of don't really like burn out anymore just because like I'm no longer like forced to do anything. I don't have, a test coming up that I have to make sure I know every single piece of material for. If something falls through the cracks here, it falls through the cracks and I'll pick it up later on when I realize it fell through the crack and I don't have that concept. But I'm not like grinding away for tests or exams or, you know, a grade rather. So it's hard for me to really give an apples to apples comparison for a lot of people that are in school that are facing burnout. One thing that I will say really helped me in school with burnout. Um, well, honestly, actually, one thing that helped me with burnout and avoid burnout kind of altogether was that I made school really like my job, right? I kind of treated school as like a 9 to 5 job, and I actually got jobs on campus within my um, selected major category. So like I got a job as the undergraduate teaching fellow for the chemistry department. So twice a week I had to run study sessions for any student that walked through my office hours. And I had to have material prepared. I had to have practice questions. I had to have keys to those practice questions. So all that alone was doing additional studying for my classes, right? It was concepts I already learned, but it built onto these larger concepts, but I was getting paid for it, right? It's a hack. I don't know why people don't get more jobs within their department as undergraduates, whether helping out or assisting in any way, shape, or form, because just by being physically around the material, you will get better at it naturally. Just think about with work. You could be like a really bad waiter, but just by being a waiter over and over and over again, you're going to naturally become a better waiter. Like just by being around the restaurant and you'll learn about the restaurant. Now, it's the same thing. And then I became a laboratory instructor for the department. So I was running the laboratories. I got really familiar with lab function, lab equipment, lab safety, everything like that. I work in a lab right now, and I've been very successful in leading teams, probably because of that goal as well. But when I was doing those labs, running those labs, I was having to make study problems, questions, read the lab, grade lab reports. All of that was compounding all that material even further. So if you're in college, that's kind of like a hack is try to like get a job for the department in some way or shape or form. And just by being around the material, you're getting paid to learn. But if you're independent for burnout, honestly, you really just have to think of it as like a pressure off situation. Like there's no rush to this there's no end game to this learning. The learning will always continue. I will always continue. There will always be another subject, in whether it be in computer science or playing guitar or whatever, that I can learn. There's always going to be another chord. There's always going to be another line of code. There's always going to be another algorithm. So why are you trying to rush through it, giving yourself unnecessary pressure, anxiety, and worry when the end is nowhere near in sight? Right? There is no end to the finish, to the race. So why are you racing? Really focus on changing that mentality from this. I'm doing this because I'm trying to find work or expenses because I have bills to pay. To I'm doing this because I like having fun and doing this because it's fun. I enjoy, improving myself and the rewarding feelings I get from actually learning the new material and seeing it conveyed in my programming. But sorry about the yap and the ramble, but hopefully that helped. Levi says this Harvard class, apparently the students were struggling. Oh, really? I didn't know that. Do you have any information where like actual Harvard CS students really struggling with these courses? Hey, Arrow, I appreciate you coming in. Are you trying to switch careers? Is that why you're doing this? If so, what type of career are you looking for? Because I know the job market for CS is horrid right now. No, I currently have a degree in chemistry and biology, and I work as a chemist. So I'm really just finding ways to, improve my education as a candidate, as a, worker, as a general person, a human being. And I just really find computer science fascinating. So that's why we're going down this avenue. Yeah, all my notes are on my GitHub for sure. All right, cool. Let's keep going here.
Key details really being malloc and one omitted detail, which we'll come back to. Yeah. A really good question. Let me summarize. If you allocate two variables that happen to be next to each other in memory, but maybe you type in, a very long string for one of them, can one overflow into the other one? Short answer, yes. And we're going to talk about that briefly today. The code I've written is not vulnerable to that at the moment. And in fact, among the things that getString has been doing for us since week 1 is it actually sort of crawls over the user's input, literally taking like baby steps to make sure that we only allocate more memory for every keystroke that you type in. So theoretically, there should be no way to crash getString unless you type in more bytes than the system has even memory for. But even that, we should be able to detect because we are somewhat inefficiently but very conservatively trying to avoid the situation you described. But it is too common in life, as again, with CrowdStrike, you'll see that humans will make mistakes when it comes to the length of memory or arrays that we have. Now, I alluded to there being one mistake or omission here. Did I somehow not practice what I preached a moment ago about malloc and its cousin? I never freed my own memory. So technically, this program has what we would call a memory leak, whereby I'm asking for memory on line 11 via malloc, but I'm never giving it back to the operating system. Now, this is a bit of an overstatement because technically when the program quits, it should automatically give everything back. But a lot of programs in the world keep running again and again and again, really forever, like a clock program or a web server or an email server and the like. And if that code that you or someone else has written asks for memory, and never hands it back, freezes, crashes eventually because the computer will somehow run out of memory. So it's an easy fix. At the very bottom of this program, once and only once I am done using t in the first place, I can simply free t. And C itself, or really the functions that we're using, keeps track of how many bytes you asked for. You do not need to. When freeing it, it will free that byte onward that you requested. So free sort of does the opposite of then malloc. All right. Unfortunately, we have so much power at our disposal now, lots of things can go wrong, but thankfully there are tools that help you find these mistakes so that if and when your program crashes, you don't have to just kind of stare at the screen or ask a TF or another human for help. You can actually use software tools that other people wrote that detect these common errors. And one of these programs that you're now going to have access to, besides printf, besides debug 50, besides the rubber duck, is a program called Valgrind, which is a command line program whose output is a little scary looking, but it will allow you to look at your program for memory-related errors. So let me go ahead and propose this. I'm going to open up a program that I wrote in advance here called memory.c. And quite simply in VS Code, it looks as follows. I have including standard I/O, I'm including standard lib so that I can use malloc. And this program does nothing useful. It just demonstrates as simply as I can a bug. On line 6, I'm allocating a variable called x that's going to be a pointer to an integer. And I'm allocating space for 3 integers. So we haven't seen this before, but it just kind of does what it says. Give me memory for 3 of these things. What are these things? Well, whatever the size of an int is, I know it's 4 usually. So I could just write 4 times 3, but I'm going to generalize it. Size of is an operator in C that lets you figure out what is the size of this type of variable. It's usually 4, but on older computers, eventually on newer computers, it might not be 4, so I'm not going to write 4. I'm going to say size of int. So this whole line 6 gives me enough memory for an array of 3 integers. And it stores the address of the first byte in a variable called x. But usually,
All right, we got to go back.
code so that I can use malloc. And this program does nothing. It knows this. Let's see. And quite simply in VS Code, it looks as follows. I have including standard IO, I'm including standard lib so that I can use malloc. And this program does nothing useful. It just demonstrates as simply as I can a bug. On line 6, I'm allocating a variable called x that's going to be a pointer to an integer. And I'm allocating space for 3 integers. So we haven't seen this before, but it just kind of does what it says. Give me memory for 3 of these things. What are these things? Well, whatever the size of an int is, I know it's 4 usually, so I could just write 4 times 3, but I'm going to generalize it. Size of is an operator in C that lets you figure out what is the size of this type of variable. It's usually 4, but on older computers, eventually on newer computers, it might not be 4, so I'm not going to write 4. I'm going to say size of int. So this whole line 6 gives me enough memory for an array of 3 integers. And it stores the address of the first byte in a variable called x. So what's x1 going to be? 72. What's x2 going to be? 73. What's x3 going to be? 33. Even in these 4 lines of code, there's 2 bugs. Can you spot any of them? Yeah. What's that? Yes, so I did not 0 index my array, so that's sort of week 2 type mistake. This should be x bracket 0, x bracket 1, x bracket 2. And there's a second, more subtle mistake. Yeah. I don't have what? I don't have room. Oh, I don't have room for the 0, but that's OK because I'm dealing with integers only. I'm not strictly trying to treat this like a string, but good eye, but only relevant if I'm dealing with strings or char stars.
So we say there's bugs here?
It's subtle, but we also talked about it like 3 minutes ago. Yeah, I didn't free the memory. So I called malloc, but I didn't eventually call free at the end of my function. So at least 2 mistakes, it would seem. Now, you can reason through this, and there's only 4 lines of code. So eventually, you'd probably figure it out with some time and practice. But could a program help me spot these mistakes? Well, debug 50 is not relevant here per se. Unless your program crashes, debug 50 can probably tell you on what line it crashed, but not necessarily why. What we need is a memory-related program called Valgrind. And to do this, to use it, I'm going to do the following. I'm going to run make memory. And if I do /memory, at a glance, nothing seems to go wrong. It didn't even crash, but it's still incorrect. And especially if I have these kinds of bugs in larger software, it's definitely going to crash eventually. So let me do this instead. Let me run this program called Valgrind on /memory. So just like you run debug 50 on /something, you run Valgrind on /memory. Let me increase the size of my terminal window, because there's going to be a lot of ugly output here for a moment, and hit Enter. And you'll see a whole bunch of cryptic output and a lot of numbers, which largely aren't useful for us until we get to the error messages. So I ran the command up here. I saw all this crazy output, but what's germane? Well, here I have invalid write of size 4. It's a little technical, but that just means I'm changing something that involves 4 bytes. Well, what does that mean? Well, apparently my mistake is in memory.c, line 9. And it's elaborating with some cryptic addresses, which, again, I don't really care about. But I do care about this. After a block of size 12 is allocated, so there's 12, like evidence that there's indeed an array of 3 ints, which total 12 bytes. So that's consistent. But what's going on? It's at line 9. Well, how did I somehow touch 4 bytes that I shouldn't? Well, if I go back to my code by shrinking my terminal window, look at line 9, it did not like, as you observed, the last element of the array because I 1 indexed instead of 0 indexed. So OK, I think my fix is going to be to change this to 0, 1, and 2. So 0, 1, and 2. But let's go back to the errors, because there was another one on the screen. If I ignore anything I don't really understand in this summary, here's something. 12 bytes in 1 blocks are definitely lost in loss record 1 of 1. More verbose than ideally it would be. But that problem seems to relate to memory.c, line 6. So I'll admit, Valgrind's output is sort of a big, complicated mess. But there are little hints of diagnostically useful information, like invalid write of size 4 and the line number of the file. 12 bytes in 1 blocks are definitely lost in memory.c and line number. So those are the kinds of things you want to look for, even if at a glance it is and will look confusing. So let me go back to now line 6. And oh, line 6, even though it's not obvious what's wrong with this line, if I'm somehow losing 12 bytes, well, it must be a memory leak. So let me just have the intuition to go in and say, oh, eventually I have to free x because x is pointing at that chunk of memory. Let me now clear my terminal window down here, make memory again, /memory, and it doesn't seem to crash still, but it is more correct, even though at a glance it seems fine either way. Let me do now Valgrind of /memory. Let me increase the size of my terminal window, clear the screen, and hit enter. And now there's slightly less output, but what I really like is the sound of all heap blocks were freed, whatever that means. No leaks are possible. And even though there's still a lot of output there, I don't see anything glaring anymore. So Valgrind 2, this week and next week, will be your friend. And all it's doing is helping check for memory-related mistakes in your code. Questions then on?
I have a question, actually. So my question is, in this example, we never declare a variable x, right? But somehow we are able to actually index into a variable x. So during the x is a pointer to a place in memory, which in itself is a variable, I guess. So you can access that point in memory as a variable. Because you have 3 of them, that's why we're able to index 3 times into it, starting from 0, and place values at that point. But nowhere in here do I call int x to declare it, other than, because it's just a pointer. So it's declared here, but so the variable itself is a pointer to a memory location. And then at that memory location, 1, 2, and 3, you just save these values here. Okay, so then in the other examples, like if you had another variable, as in, you know, int value, right? Here, you could call a pointer to this and then override the value itself, but you can just actually reserve a place in memory here, declare it in this one line here, declare a variable which represents a place in memory. Because, okay, so it still is a pointer, still is a variable, it's just a type of variable. But the int x syntax makes it look confusing, that's why I prefer int x. Oh yeah, I guess that's probably, yeah, that's a good point too. If you do it like that, it kind of makes it show that, okay, x is a variable that happens to be an integer pointer, but in itself there is no like x declaration of like a variable that points. It's interesting. Exactly, x1 is the same as x plus 1 pointer arithmetic. Try printing both. Yeah. I can't print in specifically this one. I don't have a compiler installed in my extensions here, but this is just my notes. But yeah, I get you. Okay, so do the declaration with the type. Okay, so if you're going to make a declaration, put the pointer declaration next to it, and then your variable here is equal to that place in memory, and then I reserve at memory space 1, 2, and 3 because I saved 3 spaces of size int. Okay. Well, now let me tell you this. Because I have int here, that's why I have to insert an integer here. Now, what if I were to insert a char here for x? Would I get thrown an error because I'm no longer pointing to a place in memory location that is an integer? If I were to try to save a char here. Int asterisk is the type, x is the variable name. Okay, yeah, so think of this entire thing as the type, an int pointer, right? So when you see this, just know that this means a memory location that houses integers. And then x is that memory location, and then you can put those integers at x. Perfect. That was probably a good breakdown. Okay, let's keep moving here.
Valgrind. Yeah, in front. Can you set a condition before you free the memory? You could. In this case, logically, there's no reason to, because this program is so relatively simple that I do want to free it no matter what. But you can absolutely have conditionals in there, which you might in more complicated programs. All right, well, let's play around slightly more with these garbage values to which I alluded earlier. Let me actually close this. Let me code up a file called garbage.c, just so we can make the point that there can be these so-called garbage values in a computer's memory that are really remnants of something else that has been at that location in memory before. And I can actually do this pretty easily. Let me, in garbage.c, include standard io.h. Let me go ahead and do standard io.h. Let me go ahead and do int main void. Inside of my main function, let me just give myself an array of like a lot of scores to come back to like week 2 when we introduced arrays. Suppose I very sadly have 1,024 scores to keep track of over the course of college. I now might iterate over those as follows. For int I equals 0, I is less than 124, I plus plus, and then inside my for loop, let's just blindly print out those values. %i \n scores bracket I. The problem, though, is that I have neither hard-coded those actual scores into this program like we did in week 2, nor have I prompted the user for the scores with getInt or anything else. So who knows what I'm going to be printing 1,024 times? Well, let me open my terminal. Let me do make garbage. Sort of pun intended. Let me increase the size of my terminal window, /garbage, and I should see 1,024 values that eventually will be my scores, but who knows what they are now. Enter. It's a mix of some really good and some really bad scores, it would seem. Some zeros, some small numbers, some big numbers. My God, some negative numbers, which isn't good for scores, but they're all over the place. And if I scroll up, I could count them. There's indeed going to be 1,024 of them. But they're garbage values in that I can't make head or tails of what they actually are. As an aside, this has nothing to do with C, but the operating system, Linux, that we're using here does have commands that you can run if you are getting overwhelmed by output. So for instance, if I run garbage again, if there's going to be more output than you can see at once, and you don't want to have to bother scrolling back through time, you can actually do what's called piping it to a program called less, which, as the name suggests, will show you less of the output at a time, one screenful at a time. So if I hit enter now, I only see the first screenful until I hit space, 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 and so forth, and it will paginate the output for me, and I can just hit Q when I'm done with that. So it doesn't change my code, doesn't change my program, just a handy command line trick if you're ever overwhelmed by the amount of output there. But these garbage values can really get us into trouble. And in fact, let me propose to consider another program that's a little arbitrary, but it's going to use some of today's building blocks. So here's a main function. And at the top couple of lines here, I'm doing this. I'm creating a variable called x that's going to store the address of an int. I'm creating a variable y that's going to store the address of an int. So far, so good. I haven't assigned them any values yet, but that in and of itself is not problematic. I can always assign them values later, like any variable. I'm now going to allocate enough bytes for the size of an int. You and I know it's probably going to be 4, but I'm doing it dynamically, asking for the size of an integer. And I'm storing the address of the first byte in x. But notice what I'm not doing is storing anything yet in y. The next line of code here, I'm sort of using the sentinel value 42 and storing that at the location in x. So the dereference operator says, whatever address you got from malloc, go there and put the number 42 there. This next line says, go to the address in y and put the number 13.
So this is the same thing as doing can we do this? Can we do this? Is this allowed? Anybody know? Oh, Nate, can I put char there? Can I put char there because char fits within the integer's bytes? That's why. Because char, as long as it fits within the byte range of what I allocated with malloc, with the size of, then it'll work. So this won't work, short answer. So, but But this is the same, right, as what he did before, as in, right, he did, oh, you do it before? He did this for a single value, and he said that it's like a sugar-coated way to do it. So can you... But it gets pretty complicated. So if I just had a single value here, a single malloc function with just one, to go to this memory location, I could do this, dereference it, and place that there if I weren't saving other values, right? That would work, right? Like if I just did 1 here and then save that there. All right, let's keep going.
There, but I've highlighted in red this time. Why? This line will probably crash. Why? Intuitively.
Okay, here we go. Here we go. I get. Okay, he's about to go over this right now. So, right, he declared malloc size int here, and he assigned, dereferenced it, and put 42 at x. But he's trying to do it again and dereference it again and place 13 there. Oh no, he's doing that to y though. But y doesn't have any memory associated with it, so that's why he can't do it.
We haven't given y a value. I didn't copy s's value. I didn't malloc anything for y. It contains a garbage value. Maybe it's 0 like we saw on the screen. Maybe it's a really big number. Maybe it's a big negative number. Who knows? But that's like saying go there and like put this number 13 in some random unlucky location. And again, program's probably going to crash, freeze, or something else. The other lines here are OK. Eventually, I get around to copying x into y, giving it a valid value, and then going to y's value and assigning it the number 13. So that one line of code was the problematic one ultimately. So what's nice about this code is that it actually happens to line up perfectly with a fun video that our friends at Stanford University put together that's about 2 minutes long, and it introduces a character that's well known in computer science spaces as Binky. So Professor Nick Parlante of Stanford spent some time doing some claymation to bring exactly that code and exactly that problem to life if we could dim dramatically the lights.
Hopefully it doesn't have copyright.
Hey, Binky.
Oh, it does. Okay, I'm going to move forward. It has a copyright thing. We're going to skip it.
All right, so Binky's purpose in life is really to make clear that bad things can indeed happen when you touch memory that you shouldn't, including things that we now know as garbage values. But there's even other problems, but also solutions that we now have access to, thanks to our newfound understanding of memory and in turn pointers. So it's been very common over the past few weeks, especially last week, to have to swap values. Like when we were doing bubble sort or selection sort, we kept having our human volunteers swap locations, and in the computer's memory or in our pseudocode, we had to have 2 variables or 2 values swap locations as well. For this, we thought we'd motivate folks. We can offer you either a little Mario mushroom or question mark if we can get one more volunteer today to act a little something out with me here. Don't all raise your hands at once. How about, I saw the Harvard shirt, is it? Or that shirt, yes. Yeah, no, you, yeah, come on down. Yes, the one who wanted to keep here.
Hi, my name is Gabe.
Gabe, OK, and a little something about yourself?
I live in Thayer. I'm a freshman.
Nice. All right. Well, good to meet you. Come on over here where we have 2 glasses of water. One is pink, one is blue. And each of these effectively represents like a variable that contains some value, either pink or blue. Could you go ahead and swap the 2 values of these glasses? OK. That's technically just like moving the variables around in memory. But I'd really like you to get the pink water in the blue glass and the blue water in the pink glass instead. So let me undo that.
Oh. Come on, what are you going to do? Mix them together?
You're hesitating. Why?
Because if I pour the blue in the pink, then they're going to blend together.
Yeah, and you're going to sort of overwrite the value with the other. And so we're going to lose information in that case. OK, so this was a bit of a setup. So let me get you a third glass, or a temporary variable, if you will. And if you want to verbalize how you would solve the problem now with this third variable.
OK, so I'm going to pour the blue into the new variable. And then pour the pink into my old blue cup.
Nice.
And then pour the blue back into the old pink cup.
Very nice. I think that warrants a round of applause, if we could. OK, nicely done. Thank you. OK. Which would you like?
This one.
All right, so thank you to Gabe. So all right, this was all to make the point that swapping is not that hard, and we all have kind of an intuitive notion of how to do it, but we do need, it seems, like a temporary variable. And that actually maps pretty cleanly onto C code. So how might we do this in practice? Well, if we wanted to implement an actual function in C that does swapping, for instance, I might do, if we want to actually do something in C that involves swapping, I might do something like this. A void function, because I don't need to return a value. I just need to do some work. Function's called swap. It's going to take in two values, int A and int B. And the goal in life here is to swap A and B. It's actually pretty straightforward. I could actually do lines of code like this, calling A and B the two inputs, like the pink and blue glasses, temp, or TMP for short, for the temporary variable. And just as Gabe did, I can store in the temporary variable one color of liquid, or the value of A. I can then change A to be that of B. And then I can copy the value from the temporary variable to B, and at which point I don't care about temp anymore. This code is correct. It would swap those values just as Gabe did with the glasses of water. But it's only going to work inside of the scope of swap. And this is the catch. Recall that when we introduced the notion of scope earlier, a few weeks back, we said that variables really only exist in the context of the curly braces in which they're defined, or in this case, as part of the arguments passed into the function. So this successfully swaps A and B. But if main or any other function is using swap, it's actually not going to have any useful effect on the original values of A and B. In fact, let me go over to VS Code here, where while Gabe was doing that, I whipped up this program in advance. And it looks like a lot, but it does something relatively simple. I've got main, which declares two variables, x and y, values of 1 and 2. I'm then just printing out x is this, y is that. I'm then calling a swap function. And then I'm just printing the same thing. X is this, y is that. The whole point being, hopefully it'll say the opposite the second time. What is the swap function? Exactly what I just proposed earlier, which is exactly what Gabe just did correctly with the glasses. But as you might see where we're going with this, if I go into my terminal window and say make swap, /swap, enter, it doesn't actually seem to affect the values of x and y. It does affect the values of A and B. And I can see this if I use our old friend debug50. Let me go ahead and set a breakpoint inside of swap. Let me run debug50 on /swap, enter. And just to demonstrate what's going on here, let me step through a few of these lines of code as follows. So notice one at top left. Temp has some bogus value initially. It's a garbage value. It's like putting some random color inside of the glass, but I kept it empty because in the real world, we need space for the colored liquid. But A is 1 and B is 2. Why? Because we passed in x and y respectively. If I now step over line 17, notice that temp changes to 1. If I step over line 18, A changes to 2. If I step over line 19, B changes to 1. So A and B, per Gabe's algorithm, were swapped correctly. But if I continue running this program all the way to the end, ultimately I got, because of this second printf, that x is still 1 and y is still 2. So A and B were changed clearly per the debugger, but x and y were not. So why is that? Well, it turns out that the answer to that, too, relates to memory. And code like this, at least if encapsulated in a function, is not correct, precisely for the matter of scope, because we're changing the values of variables that are local to the swap function, but has no effect on main that's actually using this function. And the reason for that is a term of art. When you pass arguments to functions, you're generally passing things by value. You are passing in copies of those values. So when you pass in x and y, you're really passing in a copy of x and a copy of y that you can do anything you want to, and we're calling them A and B in the context of swap, but that has no effect on the original versions of x and y. What's really going on, though, can be thought of again in terms of the computer's memory. So here's a chip of memory. Let's kind of zoom in and abstractly on the sort of grid as we keep describing this, and consider that we can use this memory in bunches of different ways, but the world has standardized how we use computers' memories when running programs. And we tend to use this part of memory at the top, so to speak, in certain ways, and this type of memory at the bottom in other ways. And if we understand what those ways are, we can actually infer deductively why this function is not working as intended. So it turns out, let's say even get rid of the individual bytes, because we don't really care about numbers for now. It turns out that when you double-click a program on your Mac or PC, or tap an icon on your phone, or run /something on your code space, the computer automatically loads the program's machine code, the zeros and ones that someone else compiled, or maybe you compiled, into the top of your computer's memory, so to speak. It's not literally the top, because who knows how the thing is oriented, but just for the sake of discussion up here. What else gets loaded into the computer's memory? If your program has any global variables defined outside of main, by convention, they go below the machine code that was loaded into memory. What else? If you end up using malloc in your code, that memory comes from this location here, which we didn't do until today. But actually, it turns out that getString has been using malloc all this time since week 1, because that's how we're getting an arbitrary amount of memory for everything you might type in at the keyboard. The heap, though, so to speak, grows downward. So the more and the more and the more and the more you call malloc, the more stuff that gets filled up top to bottom in the so-called heap. But there's one last region of memory, generally called the stack, much like a stack of trays in the cafeteria or dining hall, that sort of works its way up as you continue putting stacks, tray and tray and tray on top of each other. The stack, so to speak, grows upward. And the heap and the stack are used differently. The heap is indeed used for malloc, but the stack is used anytime you call a function. Anytime you have local variables, they use memory down here. So in particular, for the code I just wrote a moment ago, where I had a main function and a swap function, the stack gets used to implement this kind of logic as follows. I first, unbeknownst to me, my computer does this for me, I get a chunk of memory at the bottom of my computer's memory space that contains any command line arguments, if we had int argc and char and string argv, like a couple of weeks back, or if I have any local variables like x and y. If I then call a function like swap, swap gets its own chunk of memory, its own frame of memory above main in the computer's memory. So it's like putting down a main tray from the dining hall and then a swap tray on top of it from the dining hall. Each of them contains their own local variables, x and y here, a and b here. And you can kind of see where this is going already. If x and y live here, but we're changing a and b here, well, obviously we're not changing x and y down here. Well, let's be a little more specific. In the main function, when I have two local variables like x and y, it's like having space for them in the computer's memory. And initially, I had values 1 and 2, respectively. When I then called the swap function, that had two local variables of its own, technically arguments, passed in, which, because I'm passing by value, gets copies of x and y called a and b. But the values are going to be the same initially, 1 and 2, respectively.
OK, so is he getting to that we have to pass in the memory address of those values, or the pointers to those memory addresses, unpack the value there, or dereference the value at that address, do the swap, and then we can do it? I think he's trying to allude to that we need to actually pass in the memory addresses of those physical variable locations at that scope. Or maybe there's some sort of other functionality that happens in between.
But then in the 3 lines of code that represent what Gabe did with the glasses of water is we have a temporary variable, a third, still in the same frame of memory. And I assigned with this code here, let me
People are saying I'm right in the chat. Let's go. Man, we are getting this. This feels good.
Step out of the way. This first line of code stored the value of a in temp, like this. The next line of code stored the value of b in a, like this, at which point, unfortunately, they're identical, but no big deal, because like Gabe, we kept the temporary variable around. And then we can store the value of temp inside of b. Now, as an aside, with respect to the debugger we pulled up earlier, as well as a couple of weeks back, when you've looked at the top left of the debugger window and you can see your local variables, what you're seeing in the debugger is either these variables if you've set a breakpoint in main, or these variables if you've set a breakpoint in swap. The debugger is just showing you what variables are in scope. What does scope really mean? It's a slice of memory at that moment in time, effectively. And we've been simplifying it verbally by saying what's between the curly braces.
So do you access the heap then? Does the stack, like, so at some point, like, reach the heap? Or how does it interact with the heap?
But that's the simpler way of describing really this. Now, we don't care about temp eventually. What we do care about is having swapped these values. But unfortunately, as soon as swap returns, well, mains x and y are literally left unchanged because we only passed in copies thereof. So the fundamental problem seems to be that the swap function is logically correct, but it has not been given access to the locations of x and y in memory. What swap really needs is a treasure map, so to speak, that leads it to the actual location of x, the actual location of y, so that using like the star operator, it can go there and swap the actual values inside of main's frame of memory. So what we really want to do is what computer scientists would call pass by reference, or pass by address would be the same thing in this case, whereby what I want to do is not this code per se, which is logically correct, but doesn't fundamentally change the caller's variables, x and y. Watch the delta here. This is correct. And it looks crazy scary at a glance because there's all this new syntax, but it's really just the same syntax from the start of today used a few different places. What I'm saying now in this correct version of swap is that A is not going to be an int per se, it's the address of an int. And B is going to be the address of another int. This is my sort of treasure map whereby A and B are going to contain the addresses of x and y. What am I going to do? Well, temp is still just an int. It's still just an empty glass. But if I want to store the value at A in temp, I have to go to A and store it in temp. I have to go to B and go to A and put the latter in the former in the latter. I have to the first and the second. Then I go and get the value of temp and put it at the address in B. So exact same logic, exactly what Gabe did, just way more syntactically involved. But again, it's just using pointer declarations up here and pointer dereferencing down here to go to those locations in memory. And in fact, if I make this change in my own code here, let me go back to VS Code and let me hide my terminal. Let me make these changes. So pass in the address of an int, the address of an int, dereference A, dereference B, dereference A, and dereference B. It's almost done, but I do have to change one more line of code. And based on what we've discussed thus far, how does line 11 need to change? I no longer want to pass in x and y.
You need to pass in there
the address of x and the address of y, which involves the syntax ampersand x and ampersand y.
We are killing
so again,
this
syntactically,
lecture.
way scarier than it once was, but it's just these simple building blocks. Get me the address of x, and then go to that address as with the star operator. So let me open my terminal window again. Let me do make swap enter. It's erroring now, but why? I've made a subtle mistake. It doesn't like the fact that I've passed in the address. But wait a minute, let me scroll up. What else needs to change? The prototype here. So this also needs to be matching the actual implementation. So sort of newbie mistake, but I think now if I do make swap again, does compile, /swap, I should see x is 1, y is 2, and then hopefully, indeed, the opposite. So this version of swap correctly swaps the value because now I have a correct understanding of what is going on inside the computer's memory. And indeed, if we look at this code now in the context of the stack frames, let's see what now happens. So here is, again, the same setup. Main has variables x and y equaling 1 and 2. Swap gets called, but what are A and B? They're no longer the values of x and y, but the addresses of x and y. I don't care what those addresses are, so I'm going to abstract it away with some simple arrows. But these are sort of like the treasure map I keep referring to, the breadcrumbs, however metaphorically you want to think of it. A and B now lead to x and y. So you're passing things in by reference, so to speak, and therefore swap can manipulate those values. Now, as an aside, pass by reference is really the same idea as pass by value, but the values you're passing in are the addresses instead of the actual values. So it's sort of just context dependent as to how you think about that. But passing by reference means really you're passing in by address. All right, so with that said, step by step, what's happening? I'm going to A, which is going to contain the value 1, and I'm going to store that in temp. So what I should see in temp still is 1. Now I'm going to go to B, and what I should see at B is 2, and I'm going to put it at star A, which is the same thing as 2 here. Then lastly, I'm going to grab temp, which is 1, and I'm going to put it at B, which is like following that arrow and changing that to 1. And this then pictorially is why my new version of the code indeed works as expected. And better still, when swap is all done and that frame of memory is taken away. It's still physically there, but we don't care about it anymore, so we might as well think of it as just disappearing. The change has, in fact, permanently affected main's version of x and y. Questions, then, on this trickery?
All right, that was awesome. I really liked how that kind of was like an all-encompassing moment right there for this lecture that really kind of like helped prove that was kind of like a full circle moment, I guess, where if you were able to make that connection, you kind of understood what was talked about earlier, is that, you know, if you really understood what was going on with the pointers and with these operators, that example, if you were able to identify those errors, that shows that you're understanding this, so, which is really good, which is awesome. Would be easier to pass ampersand A and ampersand B. Yeah, exactly. You pass those in, like so. Hey, I'm really sorry if I pronounced this wrong. Boadir, appreciate you for coming in, Boadir. If you could give me a pronunciation for that name, I'd really, really appreciate it so I could get it right for you. Yeah, Anthony, the ampersand A would get the address of A, not the value. Yeah, exactly. I might have misspoke. We say here, right, the example, swap ampersand A and ampersand B, so the memory location A and the memory location B, a reference to passing by reference, passing the reference to the values of A and B variables. The swap function will dereference with this syntax to access the values at these memory locations and then perform a swap of the values at the memory locations. At those locations. All right, we're almost done with this lecture. We got about half hour left. Let's keep chugging along.
Yeah. Sorry, a little louder. A good question. When a function returns, does it stack disappear? Typically, no. You still have remnants of all of those values that were once there, unless the compiler or the computer is sort of scrubbing that memory, which is not typically done for performance reasons. And so there could be remnants of past things. So as an aside, your mind is actually going in an interesting adversarial place, because suppose there was some function that you're calling that involves passwords, for instance, and the user types in their password, and their password is stored at that location in memory. Even after that function returns, if the code is not implemented with any kind of rigor in place, you could somehow maybe, if you have malicious access to the code, access that memory location where there's the garbage value, but that garbage value is useful because it's someone's actual password. And in fact, that's a threat that has indeed happened from time to time. So here then, to recap, the bad code, but logically correct, just doesn't get the job done. The green code, of course, does get the job done for exactly those same logical reasons. But there's another problem we've now created. Even as we understand how the stack's working, and I claim that the heap is where malloc takes memory from, having like two arrows pointing at each other does not seem like a very good design, right? Because if you keep using heap, 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 heap by calling malloc a lot, you're going to eventually overflow the stack. Or if you call lots and lots and lots and lots of functions, as you might with recursion or some other technique, you might overflow the stack, like a big stack of trays eventually kind of toppling over and touching things that it shouldn't either. Unfortunately, there's no real solution because you only have a finite amount of memory, so it doesn't really matter if things go this way or this way. Eventually, you're going to either run into other chunks of memory or run out of memory altogether. So strictly speaking, this isn't such a bad thing unless you let things get out of control and you don't keep track of how much memory you're using, or defensively, make sure you're freeing it as much as you can. And there are terms of art out there like heap overflow, which means if you call malloc too many times, you might somehow overflow some other area of memory with the heap. Some of you might know a popular website called Stack Overflow. Well, what is the etymology of that website? Stack Overflow is when you call so many darn functions that they overflow each other and maybe hit the heap or overflow each other in some way. You're overflowing the memory region known as the stack. These are generally examples of what are called buffer overflows, where buffer just means a chunk of memory that you're using for some purpose. And so a buffer can certainly overflow another, especially if you're treating it as a chunk of memory this big, but you start poking around past the end of it. It's like allocating an array for 4 characters, but trying to print the 5th. or the 6th or the 100th or the 1000th, if you've not asked for it, you're overflowing the buffer you've been given. So an array is just a buffer. And YouTube and Netflix, they all have buffers in the colloquial sense, in that they might pre-download a few seconds or minutes of video, storing it in a chunk of memory, like an array, or maybe somewhere on the heap. But the point is, a buffer is a finite size, and you can potentially overflow it by going past the boundary of it, past the end, or maybe even past the beginning. And thus was the issue with the real world a few months back with CrowdStrike. So this is very popular security-related software, ironically, that a lot of the world has installed on their servers to keep themselves safe. For those unfamiliar, unfortunately, this very software crashed some months back, taking down very important systems with it, including Delta Airlines' site and so many other companies. And this cost the world millions of dollars probably in lost labor and effort because systems went down, sales were lost, human time was incurred, and it boiled down in retrospect to the stupidest of bugs, if I might say. If you read through their very long PDF, their postmortem that describes what exactly went wrong, which took a few weeks, I believe, to come out, there was this paragraph here, which actually sounds like a lot of big words. Sensors that received the new version of channel file 291 carrying the problematic content were exposed to a latent out-of-bounds read issue in the content interpreter. Like, the real interesting part is the last sentence. The content interpreter expected only 20 values. Therefore, the attempt to access the 21st value produced an out-of-bounds memory read beyond the end of the input data array and resulted in a system crash. So literally, even though you're only in a class like this for like a couple of months' time now, they had an array of size 20, and they wrote code that tried to access the 21st element. They touched memory they shouldn't have. The software froze or crashed. Therefore, the systems that self-froze or crashed and cost the world millions of dollars in downtime and other side effects because of one off-by-one error. So it's a very possible danger to trip over. And among the downsides of languages like C is that they make it very easy to do this. There is nothing in C stopping you from doing this. And a few other languages allow this as well. Other languages like Python and Java generally prevent you and me from doing this. Why? Because humans for years were writing so much darn buggy code that we realized, wow, we should probably build into the programming language defenses against this stuff. So with the right language and the right know-how, you can avoid these problems altogether. But in this particular case, they had code that similarly was not sufficiently tested. They didn't have a check 50 to tell them a priori whether or not the code was correct. And so they shipped this to computers around the world. As an aside, too, this is one of the dangers of automatic updates. If you have this on your phone or your Mac or your PC, let alone your corporate servers, if you update automatically your systems, but the update itself is buggy, you can therefore take down your whole system, personally or professionally. There's a lot of real-world implications to that business decision they made, it seems, to update so unilaterally as well.
So my question is how did a billions of dollars company have this happen? How? Like, I get the mistakes happen, but like, I mean, the quality checks, the quality assurance departments, the regulations within their own system, like, how did this even happen? Like, in terms of the business, like, how did this even get by? Like, obviously this had to have been read, this line of code had to have been passed and shipped off by multiple high-ranking officials as it made its way up to be pushed or shipped, right? So I would like to know who lost their job and at what level, because that seems crazy. Like, whoever, like, top man signed off on this push, I wonder where they are today. What do you guys think? It's interesting.
So beware, but these things happen very really in the real world. Okay, so let's take things down back to sort of like CS50 land here. Here was the functions, the training wheels that we've been using since week 1. And let's just consider for a moment how one of the most powerful of these does. Let's consider for just a moment how one of the simplest of these actually works, namely getInt. So it turns out in C, it's not that hard to get an int or a char or a float. Relatively simple, at least in a safe way. Strings are the scary one because who knows how many characters the user is going to type in. And you would seem to have to decide in advance, do I want room for 1 character, 4 characters, 100, 1,000? What if I get the number wrong and they type in a really long paragraph? Ints and chars and floats are easy because they're 4 bytes or 1 byte or 4 bytes. You sort of know in advance. So let me propose that we implement a simple program that really kind of implements the idea of getInt. So first, let me open my terminal and clear it. Let me open a new file called get.c, because I'm going to implement my own functions for getting input. I'm going to go ahead initially and actually still use CS50.h, and I'm going to use standard IO.h. And then in main, I'm going to go ahead and very simply, as in week 1, do this. Int n equals getInt, and just prompt the user for n. So nothing interesting there. And then quite simply, I'm going to print out using %i, the value of n, passing in n. So again, week 1 stuff, no memory, no explicit use of memory or pointers here yet. Make a get, /get, type in 50. Program for now seems to work. But suppose I take away truly the training wheels, not just for the keyword string, but for the getInt function as well, and I take away this header file, which means getInt no longer works. How could I implement this instead? Well, without CS50's training wheels, you can still solve this problem. You can declare an int called n, and don't give it a value initially because you want it from the user. I can then prompt the user with like a printf n : space with no new line because I just want a blinking prompt for the user, which getInt does for you automatically otherwise. And I can use a function called scanf to sort of scan the user's input for some format string. So for some type of formatted text. Maybe it's an int, a float, a string, or something else. So scanf is sort of like the opposite of printf. Printf prints something, scanf reads something from the user themselves. All right, so how can I use this? I can call scanf. I can say, what do I want to scan from the keyboard, so to speak? And I want to scan in an integer from whatever the human types. Where do I want to put that integer? Well, I can't just say put it in n, because you can't change. I want n to persist. I want to tell it to go to the address of n and put it there, wherever there actually is in memory. So again, just like with swap, if I want another function to be able to change my variable, can't just hand it the variable. I have to hand it the address of my variable. And scanf is designed to expect that. Now, as my last line, I can print out n : %i \n, and now print the value of n. So it's a bit of more of a mouthful. I've got like 2, 3 lines instead of my 1 with getInt, but I think it'll work. Let me do make get, /get, and type in 50, for instance, enter, and it does seem to work. And effectively, this is what getInt is doing. getInt's a little smarter because, for instance, if you don't type an int and you type in cat or dog or bird or something else, like weird things will happen. So we make sure that if you don't type in something that's actually an int, we prompt the user again and again and again using our own loop. So we sort of handle that error checking for you. But if I want to do this with a string, how might I go about doing this? Well, let me go back into
really quickly. So we call int n. We then say print to the screen just that prompt, basically. Scanf for %i, %integer. What is the scanf doing? So the scanf is scanning the terminal for input. It's detecting an input, and it's saving that input at this memory location of n. And then it's conveying the value here. OK.
My program here after clearing my terminal. And let me just kind of do the same thing, but with strings. I could say string s, but we know strings don't really exist as a data type. So I'm going to more explicitly say char *s. Like that's effectively a string, or a placeholder therefore. Let me print out a prompt for that string. Just say s:, just because I want the user to type in a string for me. And now I'm going to use scanf again. What do I want to read from the user? Well, I want to read a string. And so just like printf, I use %s to scan a string from the human's keyboard. And now, after that, I need a place to put it. Well, I think I want to put it in my string s. I don't need an ampersand here because s is already a char *. It's already the address of a string, if you will. But now if I go and print this, I'm going to say s
only at
%s
that first memory
\n just
location.
as before. So it's the exact same logic, but this line of code is now dangerous. And this is why we give you getString, and this is why more of the world should use libraries instead of doing this. Why is this line of code on line 7 dangerous or undefined, what it will do?
You're trying to save in a single memory location a bunch of characters.
It doesn't know where my string's going to end, or more specifically, it doesn't know how much memory is available for that string. At the moment, the only memory I've allocated implicitly is 8 bytes for the pointer called s. So I'm ready to jot down in memory where I want to put this string, but I never initialize s to anything. Previously, when I wanted to initialize s to something, I could, for instance, malloc some space. Or I could even do something like, I could specify that, oh, let's get out of the pointer business today, and let's actually just say that s is an array of like 1,000 characters, and that would mean I have 1,000 places where I can put that chunk of memory. So turns out there's an implicit relationship between pointers, as we've seen today, and arrays, whereby you can treat one as the other. But for now, let me stick with this model of making clear that I did not call malloc. And so s contains a garbage value, which is like saying put whatever the user types like over like there, somewhere random. It's a garbage value, and that's probably going to cause the computer to crash. Not always, and I don't know what to expect today, but let's try this. Make get /get enter. Let's type in hi exclamation point. I got lucky. It still worked. Let's do something random like just type a lot of characters that will hopefully overflow the buffer that doesn't even exist. Enter. Got lucky. But if I do this again and again, I know ideally that would have made an educational point, but again and again and again, eventually it will probably crash on me. It's certainly incorrect, and I bet we could figure this out with Valgrind if we start poking around with that tool as well. So what's the solution here, or what's really the issue? Well, if we consider where we started, if here's my memory, let me actually put a lot of Oscar the Grouches here to make clear that like before you use memory, it's effectively garbage values. Like who knows what is there. So in my first program, when I created a variable n, I actually used 32 of those bits, or 4 of those bytes, to put a legitimate pattern of zeros and ones to represent the number 50. So that part was good. But when it got to the string version, I allocated space for the pointer, 8 bytes, as I said earlier. But I never initialize s to anything, to malloc, to like an array, like literally nothing. So s's value is literally this sequence of garbage values, so who knows what it is pointing to. There is certainly no memory allocated elsewhere, like in the heap, for whatever the human actually types in. So this value is effectively garbage, and this is the best I could do with squiggly lines. Like who knows where it's pointing? Certainly nowhere valid. And so in this case, I got lucky. It did not crash. But the more I run the code, the bigger the input it is, odds are this will, in fact, crash ultimately on me. So how can I avoid this? Well, if I go back into VS Code, I could just allocate space myself and say equals malloc of 4. But there's still going to be a danger there, even if at the bottom I do free s, because I only have allocated space for 4 bytes. If the user types in 5 or 50 or 500, who knows what's going to happen? I'm going to overflow my buffer of size 4. I could do this another way. I don't have to use malloc. I can use week 2 stuff. I can, again, as before, just say s, maybe not 1,000, but 4. That gives me an array, which is a chunk of memory, of size 4, but what happens if I overflow that buffer? Like bad things will happen. And so this is why we still use and would encourage you to keep using getString, because it avoids overstepping the boundaries of any buffer. Like we literally, as I acted out before, take these baby steps in code, and every time you type a character, essentially we call malloc again and again and again, and it's a little inefficient, but we call malloc as many times as we need to grow enough space in the heap for whatever the human types in, whether it's...
Well, I mean, it's probably going like... You're probably doing some sort of loop and detecting each keystroke as they're inputted and reserving memory upon each keystroke live, right? So you're probably looping, scanning F, and saving if scanf detects something, malloc location proportionate to like size of char, and then keep looping for every, and keep scanning on the loop for every char input.
1 character for 4,000 or more. It's just really annoying to write out. And in fact, the code is open source, but it's a decent amount of logic just to do something relatively simple. Languages like Java, and especially Python, make life so much easier with input and output. And we'll get to that in a few weeks' time. Any questions then on scanf and really why we've been using these training wheels? Yeah. I only heard part of that. Would it be valid to use malloc and just allocate a really big number? So that just kind of like kicks the can down the road. But I bet whatever number you come up with, I could, if I copy paste enough or just type a lot, I could overflow that buffer still by just typing in longer input. And worse, you're now wasting memory because you only have a finite amount of memory. If one program is using all of this memory just in case some crazy user types in way too much, I mean, most of the time you might be slowing down the computer or at least wasting memory as well. So getString does that too. We only allocate what memory you need ultimately, even though we end up allocating and freeing a lot of memory along the way. Really good question. All right, so let's transition then to a final topic that's going to set you up really for problem set 4, in which case you'll be exploring something specifically known as file I/O, or file input and output. And we've deferred playing with actual files, where you can save files and open files until now, because you actually do need pointer syntax in C to do that with files. In Python, the world's going to be easier in a few weeks' time when you don't even need that complexity. But for now, we'll explore sort of the idea of file input and output as follows. There are a bunch of functions that come with C related to files. And here's just a short list thereof. But you can kind of infer from the names what these do in code, because they're operations you're familiar with in the real world, like opening a file, aka fopen, closing a file, aka fclose, printing to a file, aka fprintf, and a bunch of others as well. So any function that starts with an F probably means that it operates somehow on files, whether it's text files or binary files with zeros and ones. These functions tend to be involved. We'll see with this how we can now create some of our own files. So let me go ahead and do this. Let me go back to VS Code, and let's make, in the spirit of week 0, my own actual phone book in C. Let's write some code that allows me to save in a file someone's name and number so that it actually persists over time. And I'm going to go ahead and call this phonebook.c. And in this file, I'm going to include, just to make life easier still for today, because we've seen that scanf is not really your friend, we'll use getString again to include CS50.h, standardio.h, and also string.h, which might be useful. Int main void again. And inside of main, let's do this. Let's first open a file called phonebook.csv. Most of you are probably familiar with CSV files. They're like lightweight they're lightweight spreadsheet files that can be opened in Excel, Google Sheets, or Apple Numbers or the like. It just means comma separated values, or CSV. So I can make a very simple file like this myself, but the syntax is going to be a little new. It turns out, weirdly in C, there's a data type called file in all capital letters for really no good reason. I'm going to then declare a pointer called file in all lowercase, but I could call it anything I want. And I'm going to set it equal to the return value of calling fopen for file open. And I'm going to specify that I want to open a file called phonebook.csv in, let's say, write mode, quote unquote W. And I know this from the documentation for the function that W means write. And that's why I'm passing it in as the second argument. Now, let's go ahead and do this. I could do string, but we know strings aren't really a thing. So char star name equals getString, and prompt the human for their name. Then let's do char star number and prompt the human for their number. And then I want to save the human's name and number in this file like I'm adding friends to my contacts. Let's go ahead and do not printf, but fprintf, passing in file as the first argument, which is unlike printf. Printf obviously just goes to the screen by default. But fprintf needs to know what file you want to print to. I want to print out a string that looks like a string, comma, another string, and then new line. So just like printf lets you format what you're printing, fprintf lets you format what you're saving as string, comma, string, and then a new line. The last things I'm going to pass in are the values for those placeholders. Store the name and store the number, semicolon. And then lastly, let's go ahead and close the file. So it's not that many lines of code, but this is code enough to prompt the user for a new name, a new number, save. I could run it again. New name, new number, save. And just to make this clear, let me go ahead and do this. Let me open up phonebook.csv, which doesn't yet exist. Let me kind of split the screen here, which if you haven't discovered, you can do by just dragging the tabs up and around so I can see both at once. Let me do make phonebook, enter. /phonebook, enter. And I'll do, how about John Harvard, enter. And now let's see, +1, 949. What's his number? Line. Rungshan, do you remember? 2. Has anyone texted this number yet? You have it saved? This is not important, but I'd like to be consistent. Yeah. Thank you. And the 2750 spells CS50. So enter. And now notice what happened at top right. In my CSV file, I added a name to the phone book. Now let me run the program again, because there is a bug. I'll put in my name now, and I'll just do, let's see, +1, 617, 495. I think we used 1000 last time. Enter. But notice, John Harvard disappeared. And that's because I chose to write to this file. But there's another mode in which I can write data. I can actually use A for append, which is probably smarter. Let me run my program a third time and put John Harvard back. So John Harvard, enter, +1, 949. 468 2750. Oh, yes, thank you. Someone caught my mistake before I did. I didn't compile it again. OK, Control-C, make phonebook, enter. Now let's rerun /phonebook. All right, here we go. John Harvard, we'll put him back, +1, 949, 468 2750, enter. OK, that's in there. Let's run it one more time for myself. David Malin, +1, 617, 495, 1000, enter. And now it's indeed appending to the file. So if you've ever used Excel or Apple Numbers or Google Sheets and you're adding rows to the file, or you're literally clicking like new contact on your Android phone or your iPhone, effectively what's happening is Apple or Google wrote code like this to add more and more data to some file. It might not be as simplistic as a CSV file where you're separating the values with commas and just putting it in raw text. It might be some binary file with raw zeros and ones, but it's the exact same idea. And in fact, if I go ahead and try to improve this code, I should note this too. In the spirit of error checking, let me add one additional line before we add one other example to the mix. It turns out that just like malloc, things can go wrong when you try to open files. Maybe it doesn't exist. Maybe there was a typo. Maybe you are, in fact, out of memory. So here too, and for problem set 4 onward, you should get into the habit of checking return values. Don't just assume that you've got a valid return value. Check instead, per the documentation of this function, if file equals null, bad things just happened. Something went wrong, and I should probably just get out of here and return 1 or some other value instead. So again, the lesson today is anytime pointers are involved, from malloc, fopen, and other functions as well, do not trust that they are valid until you have checked whether they are null or not. All right, one final flourish here.
Almost there,
to
guys.
Implement the notion of copying a file as well. We introduced, you might have seen the cp command before for copy files from one to the other. How might we implement that ourselves, even though it's been around for some decades now? Let me go ahead and open another file here called copy.c. Or actually, we'll call it, we did copy earlier. So, did we? Yes. Let's go ahead and create a new file called cp.c to implement our own version of the copy command. In this file, let me go ahead and include standardIO.h, and let me go ahead and include another file, standardint.h, because it's something you'll see in problem set 4. And I'm going to go ahead and in int main, I'm going to use command line arguments now, int argc, string argv as an array, but we know, but we know strings don't exist, so technically main can henceforth be written as char star argv, still an array thereof. So we're just getting rid of the word string. And here's how I could open one file and copy it into another. Recall that copy works like this, cp source destination. So it's the opposite of the strcmp function, confusingly. But cp copies the source file to the destination, so you can change the name or give it any name you want. So how might I use this knowledge? Let me create a pointer called source, src for short, and open a file called, well, what should the file be called? Let's expect the user to pass in argv1, whatever the file name is, per the usage at the command line. Then let's open it up in read mode specifically. Then let's go ahead and have a destination pointer called dst for short that equals the return value of opening the second file that the human typed the name of at the prompt, and we'll open that in write mode. I'm not going to do append mode because I want to literally copy everything. I don't want to add to an existing file. And then What do I want to do? I'm going to propose that we do this byte by byte. And there's many different ways to do this. But among our list of functions from earlier are functions like fread for reading from a file, fwrite for writing to a file, as well as fprintf, which prints to a file. But if I actually am dealing with binary data, I might actually want to do this. I might want to declare a variable of type byte, which by convention, especially in the Windows world, is capitalized as byte. Give me one variable of type byte. And let me do this. While I read from the file, passing into that byte a byte from the file. So give this function the address of that byte so we can go put 8 bits in it. Then let's read in the size of a byte, which I could just write as 1, but I'm going to keep it dynamic. I'm going to read one such byte at a time, and I'm going to read from the source file. And I'm going to keep doing this so long as the return value is not 0. This is a mouthful, but allow me to just stipulate for today's purposes that line 11 just starts a while loop that iterates over the file called source, byte by byte by byte by byte, from left to right, top to bottom, so to speak. And how do I save each of those bytes to the destination file? Well, I can do fwrite, passing in the address of that byte so it can go to the location, the size of it so it knows how big it is, how many there are, which is still 1, but send it to the destination instead. And then at the end of this code, let me hide my terminal for a moment. Let me go ahead and close, for instance, the destination file, and let me go ahead and close the source file. And ultimately, I think this is enough to, again, iterate over all the bytes in the file, one byte, one byte, one byte at a time, and write them byte by byte by byte. And minor tweak. Technically, because I want to do this literally, there's no text involved, there's no Unicode. I just want this to be a raw copy of bytes. Technically, I can specify read the file in binary and write the file in binary. Don't try to do any kind of interpretation of characters. Treat it as raw 0s and 1s. And just so you've seen it, technically in C, there is no such thing as a data type called byte. This is, again, a thing in the Windows world, and we will give it to you in problem set 4. But I can actually create a type using Typedef. I'm going to have it be equal to something called uint8t, where that just means unsigned 8-bit integer. But more on that some other time, or never, perhaps. But for now, that just gives me a byte of 8 bits in a manner consistent with what Windows computers do. And if I didn't mess this up, let me open my terminal window, make cp for make the copy program, .cp. I want to run .cp, so it's my version of the copy command, not the built-in system one. Let me go ahead and copy a file like, what was the file we started with? Addresses.c. And how about we'll call this backup.c. And if I open up addresses.c here, we'll see the file with which we began class earlier. If I open up backup.c, we'll see exactly the same file. If I hold them side by side, these happen to be text, but they could have just been raw 0s and 1s. I've indeed implemented the cp command correctly in this way. Now, how, though, does this loop work? Let me go back into cp.c. Recall that I had this loop here. Let me close these other files. There was this loop that somehow just knew to advance to the next byte in the file, even though there's no +1, there's no for loop explicitly. It's just kind of reading and reading and reading until fread returns 0. Well, the reason for that is that these file reading and writing functions behave a bit like a YouTube video or a Netflix video, whereby once you start reading from them, like watching them, the sort of cursor advances from left to right. So as soon as you read a byte, the file itself keeps track of where you are in the file. Kind of like an old school cassette tape. Once you start playing it physically, the device is moving, so it knows where to read the next bytes from and where to write the next bytes to. And this is all going to be germane as we introduce ultimately a specific file format this week in problem set 4 known as a bitmap file, or BMP for short. In the world of bitmap files, you'll see that you can represent images like this, but these images are really just going to be a grid of pixels, top to bottom, left to right. And among the goals for this week is to implement some Instagram-like filters via which you can actually manipulate these images. So for instance, among the filters you'll implement is first one that converts any image, even a photo you yourself took, into black and white by throwing away color information somehow and just retaining some form of grayscale. You'll implement, and it's a bit hard to see on the screen, but a sepia tone, sort of an old school photographic style. You might be able to invert or flip the image on its axis here. So I've just reversed the sides of the bridge. Same photo, just flipped around in the computer's memory by moving like these bytes over here and these bytes over here. Or if you really are feeling more comfortable, you can do edge detection and write, no, I said that wrong. Or if you're feeling really no, wait, everyone has to do this. Sorry, let's stick the landing. We have like 1 minute left. So if what you'll also be challenged to do is blur the image too, whereby you're going to make it look fuzzier by sort of combining pixel values so that it's not quite as crisp as it originally was. And if you're feeling really comfortable, you can even do edge detection, whereby you can figure out where the outlines of physical objects are on the screen by writing more sophisticated code optionally to render images such as this here.
This
So
looks really
ultimately,
fun.
this whole
I'm
week
really
is going to be
excited to
about
do this.
file input and output,
I've always wondered how
recovering
to,
images
like,
that might have
how
been deleted or
filters were
corrupted as well.
programmatically
But we
made.
thought we'd end on a final pointer note. This is another one of these comics that now computer scientists should be able to
Such a dumb
understand the
joke.
humor of, hopefully. OK, lots of laughter. All right, that's it for CS50. We will see you next time.
Woo! All right, we finished. Oh, that was a long one. That was long. Thank you guys so much for sticking with me here, and thank you guys so much for sticking with me throughout this lecture. We watched the Harvard CS50X 2025 Lecture 4 on memory. It was a 2 hour and 30-minute lecture. It took us about 3.5 hours to get through, including stops. But I am recording alongside this entire stream, and I will be uploading a condensed version of this lecture, watch along without the breaks in between, so you can watch me, take notes live and get access to like watching it alongside with a friend. So yeah, it was really long for sure. 2 hours, like 2.5 hour lectures are pretty tough. I think after about an hour and 15 minutes, I think an hour and 15 minutes is like the sweet spot for a lecture. But like 50 minutes to an hour and 15 minutes is like the sweet spot in my opinion. But yeah, this one was pretty long. But honestly though, I learned a lot. There was not one thing I took notes on in here that I knew already. Like I learned from start to finish this whole lecture. So I will say though, because we had to learn a lot of new concepts this lecture, maybe the week 4 problem set might be a little bit more difficult for us. So we'll have to get used to this kind of this char star when representing and doing strings and everything along those lines. So just a quick reference, guys. We have a bitmap image, which is a grid of bits, zeros and ones, where zeros represent black, one represents white, kind of. We have pixel art, which is customizing individual pixels or squares of blocks of color to convey images at large. RGB, right? We learned about the hexadecimal system, which is a base 16 way of counting. It is used to kind of represent A, memory locations, and B, colors on the spectrum with the hashtag preface or the 0x preface, right? So we can actually count up to 256 total values, 0 to 255, with a base 16, with only 2 integers. Is that what it was? With byte in 2 digits. Useful because we can represent a byte in 2 digits in hexadecimal, right? So then we learned about this ampersand operator, which is just used to access the actual address in memory of that variable, and then we can dereference that operator by accessing the element at that address with this operator. And so when we declare a variable of a pointer, right, used to declare as a pointer example int of pointer p, right, when applied to a pointer in the printf, this peeks at what is at that memory location and pretty much access that actual element. And then you can use this within the printf statement to actually print the memory address of the variable, at that point. So that just kind of takes us into pointers, which are just pointing, are variables in themselves that point to memory addresses of other variables, basically. We have pointer arithmetic, so you can increment and decrement from pointers to access the next continuous place in memory. Now this can lead to memory leaks, so we need to keep that in mind. We talked about the malloc function, which is just a memory allocation function, and then you can pre-assign a various number of bytes with an input to the malloc function or a parameter assigned to it to pre-reserve that amount of data. We learned about the null, with NULL, which memory address is 0, is return if something goes wrong with malloc. And it's important that we use the free function to free up that memory after we use the malloc. We can use Valgrind, a third-party tool, to actually detect errors within our program via memory and things like that. So we can call this when running the C program. We can pass by reference of the address to actually do like things of swapping on like global versus local levels, if you have functions that do something to a variable on a local level, well, you have to actually pass in the memory of that location so it can happen on a global level across the entire program. We'll learn about heap overflow, stack overflow. I need to get a little bit better notes on these overflows. Then we talked about file I/O and bitmap files. So that was a great lecture today on week 4 memory for Harvard CS50X. Thank you guys so much. If you guys enjoyed this lecture, enjoyed hanging out with me, feel free to, please, if you could, leave it a like. It was a lot of, we streamed for a good 3 hours and 45 minutes today. So I did work a 9-to-5 job, so a lot of work today was taking place. So if you could leave it a like, that'd be great. If you feel so inclined to follow along to keep networking with me in the future, and connecting in the streams and learning alongside me, and or just learning in general, then feel free to. I love growing alongside you guys and hanging out with you guys on a daily basis. I stream every day around 7 p.m. PST. Please join my Discord link below, where I have compiled all of my study resources from all of my notes you see here, problems, projects, CS50 answers to my solutions. All of my information is in my Discord. It's a compilation of all of my study resources and a lot of other people's study resources as well. PDFs of all the books that I'm reading live on stream, from Python Crash Course to Fluent Python to data structures and algorithms that we're reading right now on stream. So yeah, the Discord is a great place to get access to a lot of resources if you're a beginner looking for some more information. But yeah, I've only been coding for 6 months, and I stream every day. So thank you guys so much for joining me here. I'm going to sign off today, and I'll be done for the evening. I do have work tomorrow, but I'll be back tomorrow around 7 p.m. PST, where we'll work on probably some more leak code. We might take a stab at maybe starting the week 4 problem set for this, or we'll probably break it up and do more work on our project in Python and other Python practice and continue on. We need to keep going with our Python project and get this one done here. I think I can probably get a working 1.0 version by the end of February, no later, with this. I think that's a good goal to have. So we have a working program here that we've been writing over the course of the past few weeks live on the channel. So if you're wanting to see that, follow along. But without further ado, I'm gonna go ahead, head out here, you guys. Thank you so much for joining me this evening. We'll be back tomorrow like usual, and I'll talk to you guys later offline in the Discord. Thank you guys. See ya.